Right now, as you listen, you are lying inside something that should not exist. The galaxy around you, the one you look up at and call home, breaks the rules of physics. It spins too fast, holds too much weight, and glows with stars that were born before the Milky Way itself even formed. By every law we understand, this place should have flown apart billions of years ago. And yet here you are, breathing quietly inside its impossible stability. A stability held together not by light, not by matter, but by something we cannot see and cannot touch. A cosmic skeleton made of darkness. If you were able to step outside the galaxy and look back at it, you would not see one peaceful spiral. You would see scars, you would see rivers of stars, long tidal streams stretching like torn seams across the night, the remnants of ancient galaxies the Milky Way devoured. Our home is stitched from the remains of smaller worlds, swallowed whole and smeared into orbit. Some of the stars shining above you tonight were born in other galaxies entirely, dragged here as prisoners of gravity. They orbit backward, off angle, out of place, like memories the galaxy could not fully erase. And then comes the quietest truth of all. You do not live in a static universe. You are inside a predator, a cannibal, a galaxy still growing, still feeding, still pulling new victims into its gravitational mouth. Even now, the Sagittarius dwarf galaxy is being torn apart, stretched thin and absorbed piece by piece. Even now, Andromeda is falling toward us. A slow-motion collision already underway, a future in which our spiral shape will vanish and be forged into something new. You are not just looking at the stars, you are inside a cosmic crime scene that is still unfolding. And somehow, out of that violence, out of that darkness, life began here, on a quiet blue world in a temporary moment of calm. But first, before we drift any further into this strange, beautiful galaxy, if you feel drawn to nights like this, to quiet wonder and the kind of cosmic stories that stretch your awareness like starlight, I would be truly honored if you would consider subscribing. If this journey speaks to you, even softly, a like or a comment helps others find their way here too. One resting mind at a time. No rush, no pressure, just a small connection in a very large universe. Now let's go deeper, into the invisible skeleton that holds our cannibal galaxy together, and the strange, soft truth of how you came to exist inside it. The light on the wall isn't just light, it's evidence. Every faint shimmer sneaking past your curtains carries the signatures of torn galaxies, mixed and blended into the Milky Way's glow. Our spiral arms look serene, but they shine with stars that began life elsewhere. Spread through the halo, looping far beyond the disk you see on clear nights, thin rivers of stars mark the paths of former galaxies that were stretched apart, wrapped around us, and left to orbit as skeletal trails. These arcs are not guesses. They are mapped threads, each one tracing the course of a victim fed to a larger system over billions of years. One of those victims still hangs in the sky. The Sagittarius dwarf is not a relic boxed behind glass. It's a live case. As it sweeps around the Milky Way, our galaxy's gravity grabs and pulls its stars, not in a burst, but in a patient peel. The streams it sheds loop all the way around us. Some arcs cross the disk, others dive through the halo and climb back out. Observatories track those stars as they leave their parent, drift into tidal tails, and blend into the background like dye dissolving in water. Each pass strips more mass. Each pass tightens the loops. What used to be a compact dwarf is now a long stream in several directions, a slow dismemberment that the night conceals, but precise measurements uncover. That isn't an outlier. The halo is busy with scars. The Gaia mission mapped motions and distances with enough accuracy to sort the sky into families by the way they move. In those patterns, astronomers found the dynamical wreck of a huge collision long before the modern Milky Way settled into a clean disk. The event has a mouthful of a name, but the gist is simple. a large dwarf galaxy, struck ours nearly head-on between 8 and 10 billion years ago, and its stars still carry the shock. Their orbits are not polite circles. They shoot outward and inward on elongated paths, many of them moving against the spin of the disk, a sign that the incoming system fell in on a different track than the early Milky Way's rotation. This crash likely helped thicken the disk and loaded the halo with stars that do not match the chemistry or the motion of the populations formed here. The halo, then, reads like a museum with labels written in orbits instead of ink. There's the Helmy Stream, a set of stars that share angular momentum, pointing back to a dwarfish system that once contained its own batch of clusters. Some estimates say a notable fraction of the halo ties back to that one event, along with a collection of globular clusters that no longer orbit a home of their own. Another shard, nicknamed Sequoia, appears on retrograde orbits too, and its debris includes some clusters with unusual chemistry and motion. Other hints point to collisions with systems so altered by time they earn nicknames like Kraken in the literature. Each group has its style, a particular spread in iron content, especially low in heavy elements relative to disk stars of the same age, or a narrow alignment in orbital tilt and energy that gives away a common origin. Stack enough of these clues, and the halo becomes an archive of swallowed neighbors. You don't need the faint streams to see the pattern. The stars themselves announce where they came from. Stars formed in small galaxies tend to be poor in heavy elements because those galaxies lost gas early or formed stars at a slower rate. They also show specific ratios among those elements. When spectra reveal lower iron but unusual balances among alpha elements, and when those same stars travel on orbits that tilt far above the disk and cross it at steep angles, you have a signature of import. That's the core method of galactic archaeology. Not digging, but reading. The atmosphere of a star keeps a chemical log of the gas it formed from, and its motion preserves the gravitational kick of its birth environment. The Sagittarius threads are easy to demonstrate. Their stars move in a pattern that wraps the sky in great circles, and their chemistry stacks up in a narrow band. Follow those lines, and you can track previous pericenter passages, see where the dwarf dove through the disk, and mark where tides cut the next wave of stars loose. Each wrap smears further. After a few orbits, former neighbors end up on opposite sides of the sky, but they still share the same orbital plane and similar energies. That's why together they draw a ring-like path through the halo. It's not the only ring. There are others, fainter, still being teased out of the noise. The delicate part is that collisions build order as well as chaos. Galaxies pass through each other. Their dark halos overlap and slow their bulk motions while their disks interpenetrate. Stars almost never hit, because even in crowded zones, the distances are vast. A sun is tiny compared to the gulf between suns. So the violence happens in gravity, not in impacts. Orbits stretch, tilt, swap energy, and form new patterns. Streams wind up in stable lanes. Disks puff up. Gas clouds are shocked and stirred, sometimes sparked into new star formation. From a backyard, this looks calm. It looks like a soft band of haze. In the data, it's a ballroom floor marked by slides and spirals where groups were folded into the whole. The Helmy Stream illustrates that elegance. The stars share a vector through the halo that is neither aligned with the disk nor random. They carry the memory of a single system pulled apart. A handful of globular clusters match the same motion and chemistry, suggesting they once orbited the lost core. The Sequoia debris tells a different story, one more retrograde and perhaps older, with a distinct chemical signature that separates it from both the Helmy group and the thick disk. Some debris may descend from an early conglomeration of building blocks before the main disk cooled and flattened. The labels are less important than the principle. The halo is compressed history. This kind of forensic work changes our sense of what we're looking at when we see a stream. It's not a decorative filament. It's a contour map of a dwarf galaxy's last few orbits. You can infer how massive it was by the width of the tail. You can see where it lost stars most rapidly by the density along the loop. And because the Milky Way's own mass distribution sets the curvature of the streams, these structures help weigh the hidden matter that stretches far past the visible disk. In this way, the faintest structures on the sky become tools for measuring the invisible shape that everything else responds to. Even the ongoing meal teaches. The Sagittarius dwarf has likely fallen through the disk several times. Each approach strips another layer. Each pass also stirs gas in the disk. Some work suggests those passages may have nudged bouts of star formation in our galaxy, a gentle push that helped ignite new clusters from time to time. Cannibalism, then, feeds growth twice, first by donating stars to the halo, and second by stirring the disk to make fresh stars of its own. You can trace at least 3 wraps in the Sagittarius stream, with stellar ages and chemistry that make sense if the dwarf was peeled over multiple pericenters. It's an ongoing, slow process, not a single burst. The big merger embedded in the halo settled differently. The incoming galaxy carried enough mass to bruise the early Milky Way's shape. Many of the stars from that event take polar orbits that slice through the disk. A significant fraction move in the opposite direction of the disk's spin. Their metal content is lower than most disk stars, and their ages cluster around a window that matches the estimated timing of the impact. Some of those stars, wave for wave, now make up a large share of the inner halo. The thick disk, which hosts older, kinematically hotter stars than the thin disk, may owe part of its existence to the kinetic energy poured in by that collision. That is not a guess from models alone. It's supported by the alignment of chemistry, ages, and orbits seen in the data. While the term museum sounds passive, the halo remains dynamic. Streams phase mix as time goes on, their edges blur, their widths grow. Ultimately, many strands will dissolve into a smoother background. But we catch some of them still crisp, still bright enough to separate from the noise. Others hide as subtle over-densities, detectable only when you add up many tracers. The map sharpens as measurements improve. Gaia's reach is wide, but faint, distant halo stars push its limits, so deeper surveys fill in the outskirts. Piece by piece, the picture turns from a mist to a lattice. Understanding the scale of these events helps ground the paradox. Collisions are common. Destruction at the level of single stars is rare. 2 spiral galaxies can pass through one another and continue on, drawn back by their combined halos until friction in their dark matter and gas finally binds them into a pair. Over long times, they merge. Bars grow, disks warp. New configurations emerge from what would look to a human like a silent passing. From a terrestrial perspective, it's hard to reconcile the quiet sky with the churn beneath, but that's the heart of the paradox. We live in a system shaped by wreckage that never looked like a wreck. So when you step outside and see a gentle glow, there's a second sky overlaying the first, a sky of memory. Threads of Helmi sweep past. The long arm of Sagittarius crosses again and again. Debris from retrograde events slides by like a countercurrent beneath a river's surface. And in that tangled net, some stars carry age tags that may reach back before the Milky Way drew a thin disk at all. If they formed in early, small fragments before our galaxy settled, and if those fragments were later torn apart and folded in, then those stars hold birth records older than their current address. That is the question that lingers as the light fades and the room grows quiet. How many of the points overhead were lit in other galaxies? How many still move on paths set by a collision that happened when the universe was young? And among them, are there stars whose ages stretch past the age of the Milky Way's own disk? Survivors from a time when our galaxy did not yet exist in its present form, now drifting through our halo as elders no one living remembers by name. Some of the quietest stars in the halo carry ages that make the Milky Way feel young. They formed before spiral arms traced their patterns, before a thin disk settled into an orderly plane. Their light crossed a universe that had not yet learned how to build heavy elements in quantity. When we study them, we find birth dates linked to an era when galaxies were only clumps, still assembling, still falling together along filaments of dark matter. These suns are older than the final shape of the home that now holds them, survivors from a time when gravity worked with raw materials and few rules beyond collapse and cooling. Astronomers call them metal poor, not because they lack substance, but because they contain almost nothing heavier than helium. Their atmospheres read like clean slate chemistry. Hydrogen and helium dominate, while iron, carbon, oxygen, and magnesium appear only as faint traces. That scarcity points to a simple truth. They formed in the first billion years after the Big Bang, before repeated cycles of stellar death could seed the gas with the elements that later built planets. In that early epoch, the periodic table had not yet had time to spread. These stars carry that signature in every photon they emit. We read those photons the way archaeologists read soil layers. Split the starlight into a spectrum and the missing lines tell the story. A weak iron line means few previous supernovae had enriched the gas. Sparse carbon and oxygen point to formation from primordial material, where only Big Bang nucleosynthesis set the baseline. The method dates stars by absence. Where younger stars show crowded forests of absorption lines from many elements, these elders show open ground, with only the lightest elements standing tall. The technique is exacting, but it turns each spectrum into a timeline. The fewer the heavy elements, the closer we get to the earliest chapters. Their orbits add another layer of evidence. Many follow long, stretched ellipses that dive through the disk at sharp angles, spending most of their time high above the plane in the halo's thin starlight. Some even move against the flow on retrograde paths that cut across the galaxy's rotation. That backward motion is not a quirk. It is a clue that they did not form in the disk at all. They likely came in with dwarf galaxies that merged long ago, arriving with their own angular momentum, their own direction, and keeping it even after their original homes dissolved. Every pass through the disk writes a shallow groove in the galaxy's memory that we can still trace in their shared motion. Globular clusters concentrate this ancient light. Each cluster packs hundreds of thousands of old stars into a sphere only a few dozen light-years wide. In their color magnitude diagrams, the main sequence turnoff sits at a position that corresponds to ages over 12 billion years. Their horizontal branch shapes and red giant branch slopes provide independent checks that agree with those early dates. The ages often stretch back to times when the Milky Way was still only a lumpy halo of gas and dark matter. These clusters serve as calibrated clocks, ticking at rates set by stellar physics rather than human assumptions, and they point consistently to a formation history older than the final disk. When we connect the chemistry to the motions, a map of early cosmic conditions appears. Low oxygen to iron ratios tell of formation before frequent core collapse supernovae could raise oxygen abundances. Shortages in neutron capture elements mark epochs before certain kinds of explosive events had time to contribute. Each element acts like a timestamp tied to specific astrophysical yields. By comparing patterns, astronomers sort stars into families, each tracing back to a different protogalactic fragment. In this way, chemical space becomes a landscape. Stars lie near one another in that landscape when they were forged by the same limited set of explosions. Distance in that space reveals different histories of enrichment and different parents. The view from Earth contains many times at once. Light from a metal-poor halo star left when the disk's spiral structure had not yet formed its current pattern. Nearby, a young blue star in the disk sends photons that began their trip only a few hundred years ago. The result is a layered sky. Some points above you show a universe that had almost no metals. Others show a galaxy already rich in heavy elements forging planets. This overlap is not confusion. It is a feature of space-time. The night does not present one moment, but a spread of moments arranged by distance. When we look up, we read time the way we read depth. These old halo stars confirm that our galaxy is an anthology. It is not one coherent tale that began in a single place and simply grew more elaborate. It is many stories bound together by gravity. Each small galaxy that fell in contributed a chapter written in low metallicity, in retrograde orbits, in the clustered ages of globulars. The Milky Way assembled those chapters into a system that looks unified from the inside. But the unity is only recent. The halo remains full of accents, patterns of motion, and chemical dialects from elsewhere, still audible if you know how to listen. This has practical outcomes for how we understand our own origin. The gas that later formed the sun did not come from a single source. It was a mixture gathered over billions of years from earlier generations of stars, some born far from the region that would become the disk. The earliest metal-poor stars did the long, slow work of setting the initial conditions. Then later, stellar deaths added the elements biology needs. Without those first quiet suns, there would be no stepping stones toward heavier elements, no enrichment curve to climb, no eventual environments with the chemistry for life. The orbital behavior of these elders also helps trace past collisions. Groups of ancient stars move together along similar elongated paths, showing where a dwarf galaxy was pulled apart. Their shared low metallicity and matching velocities act as twin signatures. Tight patterns mean a recent disruption. Wider dispersal means the merger happened long ago and phase mixed into the halo. Step by step, this lets astronomers reconstruct events in a sequence, setting dates by how stretched the debris has become and by how the chemical patterns have blended. The halo becomes a history book written in orbits and elements. Some of the most extreme cases push the limits of what we can date. Ultra-low metallicity stars approach chemical compositions so simple that they seem only one or two supernovae removed from primordial gas. These stars may record the earliest chemical footprints in the Milky Way's family line. Their scarcity is expected. Once the first massive stars exploded, enrichment happened quickly in local pockets. Finding survivors that formed before that process spread widely is rare and requires looking high into the halo, where accreted populations linger on long, slow loops. The persistence of these ancient stars raises a natural question. With such chaotic origins, why do they remain bound to the galaxy at all? Part of the answer lies in how mass is distributed. Even when accreted at odd angles and speeds, their velocities fall below the escape threshold set by the Milky Way's total gravitational well. Another part lies in how mergers proceed. Dwarf galaxies sink through dynamical friction, losing energy to the background of stars and dark matter until they disperse into streams that still share the group's original energy. Over time, the orbits randomize, but the binding remains. The halo holds them with a grip that extends far beyond the visible disk. Globular clusters offer a related stability. Tightly bound and old, they survive passages through the disk and tides from the bulge. Some were likely born within the proto-galaxy, while others came in with accreted systems. Their survival provides clear signposts of the assembly path. Count their metallicities, chart their orbits, and you find subpopulations that align with different merger events. In the aggregate, the clusters trace a scaffold on which the early Milky Way grew, fixed points that outlast the gas flows and stellar migrations beneath them. Look back at the halo with this context, and the night turns into a census of survivors. For every ancient halo star, there were many that lived and died before it, enriching the medium that later generations would inherit. For every cluster still intact, there were others pulled apart, their stars now spread across the sky. What remains visible are the fossils that resisted erasure, low metallicity suns, clustered ages, retrograde streams, and orbits that remember their first directions. This leads to a quiet paradox that helps rather than unsettles. If stars older than the Milky Way's final form still orbit within it, then the galaxy is not a finished object. It is a process. It gathers, digests, and preserves. It records its meals not with scars on a surface, but with moving traces in a vast gravitational field. The Milky Way is defined less by any frozen shape and more by the continuity of binding that links generations of stars into one system. To explain how that binding holds such diverse populations together, we have to widen the frame. The forces that keep retrograde halo stars from leaving, that let globular clusters swing past the disk without escape, and that flatten the rotation speeds across the spiral, all point to mass we do not see. Understanding why those ancient suns remain captured despite their wild paths requires stepping beyond the visible and into the invisible architecture that structures the entire galaxy. Drift up and out until the glow of the Milky Way lies beneath you like a vast spiral ship, its decks sweeping in long arcs through a quiet sea. The hull is thin, the masts are invisible, and the keel runs so deep you cannot see where it ends. It sails without wake or wind, yet everything aboard surges forward, guided by motions that never pause and a gravity that never rests. Pull back farther, and the ship shows its true outline. The bright disk is only the skin. It spins inside a much larger sphere of matter that gives no light at all. That sphere holds the ship together and stretches far beyond the edge of the starlit hull. The scale stops meaning much this high up. The luminous part measures 100,000 light-years across, yet the shadow around it spreads several times wider. What looks like a flat coin of stars is actually a razor-thin sheet nested in a broad halo, with most of the mass hiding in the dark. Here comes the first quiet jolt. Every familiar diagram of the Milky Way is a reconstruction, not a portrait. No probe has flown outside to take a snapshot. We build the face from inside by measuring how stars move and how gas glows, then solving for the shape that makes those motions make sense. It's a map drawn from crumbs on the floor, radio pulses from hydrogen, distances from flickers of variable stars, tiny shifts in position recorded year after year. Layer enough clues and a reliable outline emerges, but never an actual photograph. The ship is known by its wake. Down at deck level, the thin disk runs bright and blue-white. This is where gas stays cool enough and dense enough to collapse into newborn stars. Massive stars form here, burn through their fuel quickly, and end in explosions that write sharp knots of light along the arms. The disk stays thin because random motions are small. Stars here share a common, orderly rotation. Dust lanes thread the arms like seams, hiding forming stars and then revealing them as young clusters break free of their birth clouds. Below and above that plane, another layer persists. The thick disk holds older, redder stars, whose orbits carry them farther from the midline. They move with more scatter, as if stirred long ago. Their chemistry hints at an earlier era of the galaxy's growth, when supernovae seeded space with a different mix of elements. The thick disk doesn't shine as brightly, but it contains a substantial fraction of the stellar mass. It is the old scaffold under the new face, stars that remember a rougher time and still orbit with wider steps. At center, the ship's spine swells into a bar that crosses the core. It looks like a bulge from afar, but its inner shape has a subtle twist. If you could rotate the galaxy, the bulge would show a peanut-like silhouette, a sign of stars resonating in orbits that buckle out of the plane. In those inner few thousand light-years, gravity grows crowded. Orbits crisscross, stars move on, families of paths that loop around the bar, feed the ends of spiral arms, and help shuttle gas inward. The core's density and the bar's pattern link the center to the disk, shaping how material flows through the whole ship. Those sweeping arms aren't fixed planks you could walk along. They are patterns that move through the disk. Where gas encounters the pattern, it slows and piles up. As density rises, gravity takes hold, clouds collapse, and young stars turn on, marking the arm with bright knots of blue light. Then both stars and gas drift on, leaving the arm's crest and rejoining the spaces between. The pattern survives like a wave moving through a crowd. Massive stars die in place, painting the arms with supernova remnants, while smaller, longer-lived stars move on and blur the edges. Our address sits away from the traffic. The Sun orbits in a minor spur between larger arms, roughly 26,000 light-years from the center. This quiet lane sees less frequent bombardment by nearby supernovae and fewer giant clouds that could disturb the solar system's orbit. The view here is broad. The galactic center hangs low on the horizon of our night, and the arms present as sweeping currents rather than tightly wound storms. Over long times, even this suburb shifts, but for now it offers a stable neighborhood where subtle motions add up unnoticed. Nothing in this ship stands still. Stars stream like silent currents. The disk rotates once every few 100 million years. Even the arms drift relative to the stars inside them. The bar tumbles slower than the disk turns and exchanges angular momentum with the surrounding matter. If you tried to wait for a complete turn, whole continents would move on your homeworld before the galactic clock ticked once. You never notice the motion because everything nearby shares it. No wind presses your face and no corner creaks. Because we sit inside the disk, we learn its structure by tracing signals that pass through dust. Neutral hydrogen emits radio waves at a precise frequency when its electron flips its spin. Those waves pass through the dark lanes and carry velocity information through the Doppler shift. Carbon monoxide marks denser molecular gas, and its faint glow shows where clouds gather. Infrared light reveals stars hidden by dust and visible wavelengths. Parallax gives precise distances to nearby stars, and the dimming of standard candles steps us farther out. Stitch all of this, and the ship's blueprints come into view. The disk is not cleanly flat. One edge warps up, the other down. Part of the outer disk lags and flares thicker than the rest. The arms differ in brightness and length. The bar is slightly off-center relative to the outer gas. These asymmetries likely come from nudges, past mergers that stirred the disk, or the pull of nearby dwarfs. The disturbances persist for hundreds of millions of years and can seed new waves that move through the gas. What looks like imbalance near the edge can be the sign of an ongoing conversation between the ship and its surroundings. Lift your gaze beyond the disk, and the halo becomes clear in its emptiness. Sparse stars and ancient clusters float there, spread across a volume far larger than the disk itself. Their orbits dive in and out at steep angles, and their chemistry often marks an origin in smaller galaxies that fell in long ago. Most of the mass in that region doesn't shine at all. Its presence shows up in the speeds of stars and in the way satellites orbit. The halo sets the stage, supplies the gravitational well, and slows the disk's spread. Within the disk, gas follows the pattern set by these larger structures. Spiral density waves gather and release it. The bar channels it inward, where pressure and turbulence rise. The central few hundred light years host dense molecular clouds, star clusters, and complex magnetic fields. The supermassive black hole sits at the very center, but most of the inner structure runs on the collective gravity of stars and gas. Energy flows from supernovae and stellar winds stir the medium, while gravity tries to calm it. The shape we see is the balance of these opposing pushes. Young star clusters light up along arm segments like strings of lanterns. Many are short-lived as coherent groups. Differential rotation shears them apart. Associations dissolve, and their members spread into the background population. Open clusters that survive do so by holding on to enough mass to resist tidal forces as they orbit. Their distribution along the arms helps trace the pattern speed and the locations where gas piles up. As they age, their integrated light reddens, and their orbits can drift higher above the plane if disturbed, feeding the thick disk over time. Giant molecular clouds serve as the fuel tanks. They span tens to hundreds of light years and carry enough mass to birth thousands of stars. When a cloud meets a spiral arm, shock fronts and compression raise density. Feedback from the first massive stars then both ignites and curtails further star formation. Ultraviolet radiation carves cavities. Supernovae can trigger collapse in neighboring clumps while blasting others apart. This balance between triggering and quenching controls how the ship builds new stars without exhausting its gas too quickly. From far above, the arms show subtle branching. Segments split, fade, and reconnect. Dwarf companions tug on the outer disk, creating kinks and ripples that propagate inward. Resonances between the bar and the disk set preferred radii where structures pile up or clear out. The co-rotation radius marks where stars move with the same angular speed as the spiral pattern, creating quieter lanes where gas lingers longer. Farther in, inner Lindblad resonances help shape rings and gaps. The ship's pattern is a set of overlapping rhythms. Even the dust has its lanes. It absorbs starlight and re-emits in infrared, carrying away energy and cooling gas enough for collapse. Its distribution maps the coldest parts of the disk and the outlines of the arms. Where dust thickens, starlight dims and reddens, altering our view of distant parts of the ship. Correcting for those effects is part of how we rebuild the map from inside. Without that correction, the core would look dimmer than it is, and the outer arms would seem to end early. Our quiet perch inside the Orion spur places us in a patchwork between larger routes. Upstream lies the Perseus arm, downstream the Sagittarius arm. Over time, the sun drifts relative to these structures, crossing arm segments and leaving them behind. The spur itself is a bridge of star-forming regions and clusters, not a full arm, but it functions as a stable neighborhood over long spans. Nearby gas clouds set the recent star formation history around us and trace small-scale feedback loops between young stars and their parent material. The ship sails through space with no shore in sight. Its hull bends, its decks sway, and its crew moves to rhythms we only learn to hear by measuring faint shifts in light. Nobody will live to watch it complete a single turn, yet we can name the parts, infer the forces, and mark our place on its chart. A long circle begins beneath our feet and will not close for hundreds of millions of years, so the clocks we carry in our heads won't do. Out here, a year means something else entirely. While you sleep through a single night, the sun carries you almost 12 million miles around the galaxy. That motion never pauses. Earth spins, orbits the sun, and the whole system rides a larger path around the Milky Way at nearly 500,000 miles per hour. You don't hear it, you don't feel it. But space is motion, layered on motion, and your bed is part of a great curve that keeps sweeping forward even as your room stays still. One lap around that curve takes on the order of 225 to 250 million years. That span has a name, a galactic year. Every story humans have told, every city built and abandoned, all the births and endings you could stack into our written memory. Those fit into a sliver of that circle so thin it would look like a pencil mark drawn across the rim of a stadium. The sun has completed only a handful of these orbits since it formed. It is a long commute through a structure held together by gravity and a lot of time. Think about where that places us. The last time Earth moved through this same slice of galactic space, the continents sat in different arrangements and life on land followed other rules. The ground itself shifted while the sun kept turning. Over one orbital arc, oceans opened and closed, mountain chains rose and wore down, and the sky filled with species that vanished long before your ancestors appeared. The galaxy moves at a scale where geologic calendars start to read like journal entries. Yet you don't feel any of this because space offers no friction to mark the journey. The solar system rides a clean, almost circular path. No roaring wind, no rumble of wheels. Gravity bends space, and the sun follows that curve as if it were the most normal thing in the world. The steadiness is what hides the speed. Constant velocity is quiet, with no stop and start to announce it. The motion disappears into daily life. That smooth circle is not perfectly flat. The sun also bobs up and down through the galactic plane, taking on the order of tens of millions of years to complete a single vertical oscillation. It moves above the disk, slips back through it, and dips below, crossing different layers of gas, dust, and stars. This long sway means our neighborhood changes with time. We pass through slightly denser regions and clearer ones, through areas with more star formation and areas with less. Across many cycles, that shifting environment may nudge the flow of comets, stir clouds, or alter the background radiation that washes over Earth. The point is simple. Our path snakes. It does not trace a single perfect ring. The stars around us do not all share our speed or direction. Some move ahead, some lag behind, and some cut across our lane. This is where spiral arms become less like rails and more like traffic. Spiral arms persist because they are patterns, not fixed piles of the same stars. They act like slow pressure waves drifting through the disk, compressing gas as they pass and sparking chains of star birth. Newborn clusters light up the pattern, then age and fade while the wave continues on. We drift through these regions. Sometimes we approach a spiral arm from behind and overtake it. Sometimes it catches us. The stars within the arm also move, but the pattern holds, the way a congestion zone on a highway can creep along independent of any single car. Now widen that to a city scale. The galactic bulge is a downtown where stars crowd together and orbits cross. The inner lanes are busy and bright, full of short-lived, massive stars that burn hot and expire in violent ends. Out here, where we live, the lanes spread out. We sit in the Orion Spur, a quieter side street between major arms. The flow here is slower, the intersections less frequent, the risk of close encounters lower. Farther out, the suburbs thin into lots with more space between neighbors, and the outskirts edge into darkness. Over millions of years, the traffic patterns change as arms drift and as stars migrate from their birthplaces. But from night to night, it is stable enough to sleep through. Each mark on your wall calendar sits on a unique patch of this route. Every birthday candle you blew out burned in a spot we crossed once and will not revisit. Human lifetimes are points, not loops, on this map. That does not make them small. It gives them texture. The fact that this precise arrangement of stars, clouds, and background radiation exists only once means your present is specific in a way that feels personal, even if the scale dwarfs us. The solar system's path also swings slightly in and out from the center over very long timescales. That radial motion is modest, but it matters because the galaxy's gravitational field changes with distance. The density of stars, the pressure of gas, and the average radiation background all grade from the core outward. As we drift, we sample different mixes of these conditions. Tie that to the vertical bobbing and the traffic-like flow of spiral patterns, and you get a route that is quiet but not monotonous. The sun is a steady driver, yet the scenery shifts. You can see pieces of this drift written in the sky as stellar streams, long ribbons made of stars sharing common motion. Those streams mark remnants of old star clusters and dwarf galaxies torn apart earlier in the Milky Way's life. They cross our path at angles, their members moving together like commuters from an old road folded into the current grid. When we pass near one, the relative motion shows up in careful measurements as a change in star velocities. The shape of those flows helps confirm the larger pattern. Stars do not move in lockstep. They weave. Differential rotation is the quiet engine behind that weaving. The inner regions orbit the center faster than the outer regions, but not in the way planets orbit a star. The galaxy's rotation stays remarkably flat over a wide span of distances. That means the outer disk moves nearly as quickly as the inner disk, creating shear that stretches structures into spirals without tearing them to shreds. The result is a long-lived, shifting architecture that looks stable on human timelines and fluid on galactic ones. For a family on a planet, the benefit is calm. For a scientist, it is a system where predictable patterns and subtle deviations both matter. Think about the vertical crossings of the disk. Each passage through the plane takes us through a layer with more gas and dust. Over millions of years, that can alter how many cosmic rays reach Earth and how often comets get nudged from distant reservoirs toward the inner solar system. The research that looks for links between these cycles and events on Earth is ongoing. The timescales match well enough to make it worth asking the question, but the galaxy is complicated. The important point is that the solar system rides a three-dimensional route, and that route has seasons you could only notice from a timeline that ignores centuries and cares about tens of millions of years. Meanwhile, back at human scale, nothing in your room changes. The clock ticks, the air settles. Yet at that same moment, our star is cruising past other stars that also cruise, all of them tracing orbits cued by an invisible mass distribution. Some neighbors pull away and become strangers. Others drift closer for a while, then slide to different lanes. Star clusters born together disperse over a few 100 million years, their siblings blending into the background until only chemistry and careful measurements can reveal their shared origin. The speed we carry creates a paradox of comfort. Moving that fast might sound dangerous, but constant motion keeps the solar system safe from the kinds of jolts that a stop would deliver. No sudden deceleration, no sharp turns, just a wide bend and a slow nod through the disk's thickness. The quiet is what makes life possible. Stable orbits allow climate to settle into patterns over long enough spans for oceans and ecosystems to develop and persist. If you step outside late at night and look up, the stars appear fixed. Over thousands of years, constellations glide, but the motion is so slow that drawings passed down from ancient observers still make sense. That apparent stillness is a trick of scale. We are surfing a current so smooth that it looks like a lake. From outside the Milky Way, our path would draw a clean ribbon around a bright core. From inside, the ribbon looks like a sky that simply is. So the peace you feel at night is not the absence of motion. It is the product of motion that never stops. The sun carries us through star-filled currents without jostle or noise. Long after every landmark from our history has eroded, the orbit will continue, and other minds may mark their own moments along this same route, under different constellations and different skies. There is one more quiet fact embedded in this ride. When astronomers trace speeds across the disk, they find that the outer parts move almost as quickly as the inner parts. That flatness holds steady over distances, where gravity from visible stars and gas should drop away. If everything orbits this fast, and the edges keep pace with the center, then by ordinary expectations, the galaxy should have spun itself to pieces. Here's the part that refuses to behave. The outskirts of the Milky Way move too fast. Stars, tens of thousands of light years from the center, tear around the galaxy at nearly the same speed as stars much closer in. By the rules you learn from planets circling the sun, outer orbits should crawl. Gravity weakens with distance, so velocity should drop. Yet the line stays stubbornly flat. The edge runs as fast as the heart, and the math we use for everything from rockets to tides stares back and says, this shouldn't happen. If the galaxy contained only what we can see, stars, gas, and dust, the outer regions would feel too little pull to keep them bound. Centrifugal force from their motion would overpower gravity. Over billions of years, the Milky Way would shed its outskirts like a spinning lawn sprinkler flings water. You'd expect a dense, compact center surrounded by a famine of stars. Instead, we find a grand, persistent disk with spiral structure that holds together across vast distances and long timescales. The visible mass can't supply enough gravity to explain the observed speeds. Something else must weigh down the system. Astronomers tested the expectation in the simplest way possible, measure speeds at different radii, and plot them. The results should dip as you move outward, similar to how planetary speeds fall off in the solar system. But when the rotation curve is traced across the Milky Way, the decline never comes. The curve runs flat. This isn't a quirk of one direction or one type of star. Gas clouds, young stars, old stars, tracers that sit far above the disk. Across methods, the same pattern appears. An orderly gradient gives way to a stubborn plateau that forces a new conclusion. Most of the galaxy's mass does not shine. The solution that holds up across different galaxies and different measurements is an invisible component that pulls with gravity but does not emit or absorb light. Call it dark matter. Add 5 to 6 times more mass in an extended, roughly spherical halo surrounding the visible disk, and the numbers fall into place. The flat curve becomes expected, not weird. Outer stars can race without leaving because they're running inside a deep, hidden, gravitational well. Spiral arms don't unwind because the overall pull of the halo keeps the disk coherent. Star-forming gas stays bound, allowing long cycles of birth and death to proceed. Think of it as a framework that sets the stage before a single bright star turns on. The luminous disk lives inside this larger, transparent structure. The halo stretches well beyond the furthest visible stars, encompassing the satellite galaxies and the diffuse streams that thread the outskirts. It doesn't clump into bright knots like normal matter, because it does not interact with light or with itself in the same way. It appears smooth on small scales and dominant on large ones, shaping orbits while remaining untouchable to telescopes built to collect photons. Other galaxies show the same stubborn rotation, small or large, barred or unbarred. When their speeds are mapped, the outer regions move too fast to be explained by starlight and gas alone. The pattern repeats so consistently that it becomes a diagnostic. If a galaxy has a flat rotation curve, it holds a massive, unseen halo. The Milky Way is not an outlier. It is an example of the rule. The universe, at this scale, is organized by something we infer only through its pull. In rare cosmic collisions, the hidden mass reveals itself by where it does not go. When two galaxy clusters pass through each other, the gas in them slams together, heats up, and lags behind. The stars mostly sail through because space is wide and stars are small targets. The mass that keeps pulling on the stars, inferred by how it bends background light, follows the stars rather than the gas. The separation between light-emitting gas and gravity-tracing mass maps the invisible component. It behaves as if it interacts very weakly with normal matter and with itself, gliding where gas sticks, making its presence known by how it warps paths without shining. For the Milky Way, this hidden scaffold clarifies several puzzles at once. The outer disk does not evaporate. The spiral pattern can persist for billions of years because the gravitational environment remains deep and steady at large radii. Star-forming regions stay bound long enough to cycle gas through generations of stars, enriching the interstellar medium instead of losing it to space. Even the broad shape of the disk and the orbits of satellite galaxies are consistent with a dark halo that outweighs the luminous parts by a wide margin. Without that halo, the elegant order you experience as the calm night sky would not exist for long. What exactly fills that halo remains an open question. The name is a placeholder for an effect we can measure with precision, but do not yet understand in detail. One path imagines new particles that rarely touch ordinary matter. massive, slow-moving constituents that pass through stars and planets like ghosts, tying the galaxy together through gravity alone. Another path looks to ultralight particles that might form large, diffuse fields. Others consider neutrino-like particles with unusual properties. Each option carries testable consequences for how structure forms, how the early universe cooled, and how small-scale features appear in galaxies like ours. There is a different approach that tries to keep all the mass visible by altering how gravity works at low accelerations. Change the law, not the contents. Modify the equations so that a galaxy's outer parts can stay bound without extra matter. These ideas have had success fitting some rotation curves, and they encourage careful tests. But when you stack galaxies into clusters, when you watch how mass distributes in collisions, and when you weigh the universe through its background radiation and large-scale structure, a single adjustment to gravity struggles to account for the full set of observations. The simplest, most flexible explanation that fits across scales still points to unseen mass. Back in the disk, the presence of the halo sets the tempo for everything else. The sun's orbit, the bobbing motion above and below the plane, the long-term stability of spiral arms, these rest on a gravitational bed that is thicker and more massive than any map of stars suggests. Even the streams from cannibalized dwarves trace paths that reveal the halo's shape. Their arcs, kinks, and dispersions are like dye poured into an invisible current. By fitting those patterns, astronomers refine the profile of the halo and estimate its total mass. The answer keeps landing in the same range. The dark component outweighs the luminous one by a large factor. Because the halo reaches far beyond the bright disk, it also governs the orbits of our satellite galaxies. The Magellanic Clouds, the Sagittarius Stream, the ultra-faint dwarfs that barely make stars at all. Each moves within the larger gravitational field. The hidden mass binds this family together and slows their escape. It also sets the stage for the future meeting with Andromeda, whose own halo is already touching ours in the darkness between. Long before stars mingle, the halos interact, shaping trajectories and exchanging energy like two vast, overlapping atmospheres. On human timescales, the stealth of this framework can feel unsettling. We are used to seeing what influences us. Here, the main driver is not just dim, it is fundamentally transparent. We detect it by its pull on things that do shine. The rotation curve is one measure. The swaying of streams is another. The thickness of the disk, the motions of gas, the dispersion of stars at different heights above the plane. They all carry hints of the halo's depth and shape. Each new dataset adds another constraint, and the picture sharpens without a single photon from the missing mass. The consequences flow down to everyday scales. The heavy elements that make planets and people accumulate only when gas stays bound to the disk long enough to cycle through many generations of stars. If the outer galaxy lost its material early, the reservoir feeding star formation would have run dry. The halo's grip preserves the raw ingredients across billions of years, giving time for complex chemistry to develop in quiet neighborhoods like ours. In that sense, the dark framework is not only a structural necessity, it is part of the precondition for life in a spiral galaxy. If you step back to the largest scales, the same invisible scaffolding appears in patterns of galaxies across space. Filaments thread the cosmic web, with galaxies beating along them like dew on wires. The mass in those filaments is dominated by the unseen component. Gravity collects the luminous matter into the deeper wells, carved by the dark backbone. Our home galaxy, with its bar, its arms, its quiet suburbs and violent core, is a local expression of that wider architecture. The web holds, the halos bind, and inside them the bright parts settle, spin, and build. All of this returns us to the paradox that started it. The Milky Way holds its shape because it is heavier than it looks. The laws remain intact. Our inventory was incomplete. With the hidden mass restored to the ledger, the motions that seem to break physics become the expected outcome of a much deeper gravitational field. In the dark, the galaxy finds the strength to endure, and that raises a new curiosity. If the invisible halo secures the outer reaches, what rules the inner extremes where the pull grows strongest and light itself can lose the race to escape? The same gravity that keeps the disk from spilling into space also sharpens to a point near the center, where orbits tighten and space-time bends. We've tracked stars in the core across years and seen them whip around an unseen mass with breathtaking speed. The farther inward you look, the more the calm rules break, and the more the galaxy reveals the engine it hides at its heart. You feel the pull long before you reach it. 26,000 light-years away, gravity starts to change character. It stops behaving like a gentle curve you can coast along and tightens into a grip. Near the center, speed becomes language. Space starts to count in orbits and periapsis and tiny deflections that add up. We don't see the source. We see what it does to everything around it. In this direction, night takes on weight. The mystery revealed itself through motion. Astronomers aimed at the crowded heart of the Milky Way and watched a swarm of stars draw tight loops on the sky. They traced ellipses small enough to fit within our solar system. Some of those arcs shifted measurably in hours. Years would make sense. Hours do not. The only way to make those paths work is to put 4 million suns in one compact point. That mass fits into a region smaller than the orbit of Mercury, hidden because light cannot escape. You never see it directly. You watch its gravity write signatures on the stars that pass nearby, and the math refuses any other answer. And yet the image we carry of a monstrous feeder doesn't match the behavior we find. Sagittarius, a star, sits quiet most nights. It flickers. It burps radio and X-ray flares, but for the scale of its mass, it dozes. The stars pay respect anyway. The innermost ones race like clock hands you can watch move between observations, their paths precessing under the intense pull. The paradox becomes clear. The object at the center is not an all-devouring mouth. It is more like a conductor keeping time, holding the innermost lanes in order so the rest of the city can function. That order shows up in structure. Gas flows inward along the bar, that elongated spine slanting through the core. The bar feeds the center and helps seed spiral patterns farther out. Around the black hole, matter forms an accretion flow, thin and hot, glowing in radio and infrared. You can think of it as a dim ring pushed and twisted by intense gravity. The material does not glide in. It collides, heats, and sheds angular momentum through magnetic turbulence. Viscosity at these temperatures is not like anything in daily life. It comes from tangled fields and charged particles dragging on one another. All of it circles an event horizon that sets an absolute edge. Cross that boundary, and light cannot bring news of what happens next. The center hasn't always been quiet. When you look above and below the plane of the galaxy and gamma rays, two enormous lobes rise like mirrored smoke. These are the Fermi bubbles. They stretch tens of thousands of light years. Their edges are sharp. Their energy tells a story of a past outburst from the core. Whether it came from a burst of feeding at the black hole or a storm of star formation packed into the central region, the effect is the same. For a time, the heart of the Milky Way ran hot enough to light up gas far into the halo. Those lobes remain as an afterglow, a memory in high-energy photons and shocked plasma. It helps to sit with the idea that darkness can enable order. Remove that 4 million solar mass anchor, and the inner bar loses a major part of its balance. Density waves that organize gas and stars into spiral patterns weaken. The flow of material that fuels star formation changes shape. Step back, and the consequence becomes personal. The conditions that led to the cloud that formed the sun depend on long-lived patterns in the disk. Those patterns trace back to the weight at the center and the skeleton provided by unseen mass throughout the halo. The calm of our neighborhood uses the core's mass as one of its constants. Close in, the core behaves like weather. Gas streams in lanes and filaments. Plasma winds shear and fold around magnetic fields. The fields twist, reconnect, and fling energy into the medium. Stars follow orbits that cross and tilt. Some sweep so close to the black hole that their paths bend notably within a single night of observations. Others pass by companions, exchange energy, and change lanes. Old red giants crowd the region, their envelopes pocked by outflows and radiation. New stars form in compact clusters under pressures far higher than the quiet suburbs of the disk. Gravity focuses these processes, but it doesn't dictate a single, smooth flow. It sets the arena and the rules, while turbulence plays the game. There is spin at the center. Rotation drags space-time close to the horizon. That frame dragging adds a twist to the orbits and the flow of the accretion material. Where the flow lines up with spin, material can linger and gradually sink. Where it fights, heat and instability rise. All the while, the accretion flow remains weak by quasar standards, which is why the skies above Earth stay dark and safe. Even so, the core can spit out flares when clumps fall inward. Those flashes arrive across the spectrum, short and sharp. They tell us how matter behaves when gravity claims the final say. Stars interact with this machinery in ways both subtle and violent. A tight binary that strays too near can be torn apart, one star captured into a close orbit, the other flung away at escape speed. That is one path to a hypervelocity star, the kind that leaves the Milky Way altogether. Giant molecular clouds drift by and shape the fuel supply. When a new batch of gas feeds the bar feeds the core, and the core responds. The timeline for these episodes runs long compared to human life, but the effects accumulate. You read them in the kinematics of bulged stars and the distribution of gas lanes cutting across the inner few thousand light years. In the crowded center, radiation shapes chemistry. Harsh ultraviolet light strips electrons. X-rays puncture deeper and heat small pockets. Dust grains absorb and re-emit energy, setting temperatures for collapsing clumps. The mix of heavy elements there differs from the outer disk. Those differences track the star formation history of the inner galaxy, and this chemical map tells you where and when stars formed in past bursts. The black hole's quiet periods and active phases leave fingerprints in that map. You follow those clues the way you follow a weather system by its pressure fronts and temperature gradients. If you stand back at the scale of the whole galaxy, the core's mass acts like a boundary condition in a model. Set that value, and the equations of motion for the bar and spiral density waves align. Set it differently, and the simulation builds a different city. We don't live in an abstract model, but the match between models and the Milky Way's observed shapes points to the same story. A central weight, not ravenous, not absent, shaping the traffic. When you hear black hole, you might expect a simple story of consumption. What you find instead is a system that turns gravity into structure. That structure guides fuel toward star-forming regions, then star death returns heavy elements to the gas, then new stars and planets condense from that enriched mix. The weakest link would break the chain. Without the anchor, the bar falters. Without the scaffold of unseen mass in the halo, the outer disk won't hold together. The core and the halo speak to each other through gravity, and the disk translates that conversation into stars. The motion in the core never stops, but it also rarely explodes. A balance holds between inflow and heating, between magnetic stress and radiative loss. That balance looks fragile from a distance. Up close, it proves robust across long ages. You can see it in the lack of a current quasar-level blaze. You can see it in the constrained wobble of nearby stellar orbits, which keep time like a carefully tuned mechanism. The central region is energetic and noisy, but it adheres to its own steady rules. We owe part of our quiet to that steadiness. A core that erupted frequently would fill the inner galaxy with ionizing radiation and fast winds far more often. The Fermi bubbles tell you that outbursts happen, but not all the time. Our disk has had long stretches to settle, form clouds, and light new stars without constant disruption from the center. The history of Earth fits inside that allowance. While the core's metabolism ticked along, the outer disk prepared chemistry and time for life. Look back toward the inner glow and you can feel how the pieces connect. The dark halo holds the outer city together. The bar channels gas toward the middle. The middle keeps time and mass in balance. When we map where stars live, how they move, and what they're made of, this structure emerges from the data like a blueprint. There's no ornament here. There's a weight at the center, an engine starved to a quiet idle, and a city that runs because it exists. The galaxy does not advertise any of this to the naked eye. You see a band of milky light and a bright bulge where the center lies hidden by dust. Behind that dust, gravity operates at full intensity. The orbits near the black hole close and precess and nod in ways that let us test our theories of gravity. Each measured star acts as a probe that lights up the field. Those measurements confirm the mass, the compactness, and the character of the core. The core, in turn, anchors the wide, flat disk whose edges spin too fast for visible matter alone to hold. Two unknowns, one invisible and diffuse, one invisible and compact, cooperate to make a galaxy that stays in one piece. Move away, and the sense of scale returns. The inner few light years pack in stars by the thousands. Beyond that, the density falls as you move into the bulge, then the bar, then the disk. But the influence of the central mass persists much farther out than the light it emits. It sets the central potential. It nudges the distribution of orbits in the bulge. It interacts with gas flows that reach thousands of light years. It sits at the nexus where many processes meet and trade energy, momentum, and matter. The space between stars is not a void. It's an ocean with currents, pressure changes, and storms that play out over light years. Astronomers call it the interstellar medium, and it behaves like weather stretched across a galaxy. Gas flows, dust drifts, radiation pushes and sculpts. Gravity gathers the loose material into knots and filaments, then tears it apart again. Over time, this sea sets the pace of star birth and sets the limits on how far light can travel before it is absorbed and re-radiated in longer wavelengths. Across this ocean, clouds take on different states. Some regions are warm, thin, and transparent, where atoms of hydrogen and helium move freely and rarely collide. Others are cold and dense enough to turn hydrogen into molecules. These molecular clouds span dozens to hundreds of light years, with total masses measured in thousands to millions of suns. Dust grains, tiny mixtures of carbon, silicates, and ices, float within them, blocking starlight so completely that the clouds appear as black patches against brighter fields. The darkness isn't empty. It's a sign that photons can't get out. Infrared and radio telescopes pull back the curtain, revealing dense webs and knots where stars begin. The paradox is that this darkness looks calm. In reality, it churns. When a massive star ends its life, the shock wave travels through the surrounding gas at supersonic speeds, heating and compressing whatever it hits. Ultraviolet light from young stars carves out cavities and shells, driving expanding fronts that reshape nearby clouds. This radiation strips electrons from atoms, making H2 regions that glow as the electrons recombine, producing the familiar red and green emission we see in long exposures. Magnetic fields thread through all of this, guiding charged particles, resisting collapse along one direction while allowing it along another. The result is a tangle of filaments, sheets, and bubbles that looks messy, but follows the quiet rules of pressure, gravity, and magnetism. Stellar nurseries emerge where gravity gains the upper hand. In the coldest corners of a molecular cloud, turbulence creates dense clumps. As they grow heavier, their own gravity deepens, pulling in more gas and dust. The cores inside these clumps warm from compression. When the central heat and pressure reach the threshold for nuclear fusion, hydrogen begins to merge into helium. A star turns on. Before that moment, jets stream from the forming star's poles, clearing cavities through the cloud and lighting their walls. Once a cluster of stars has formed, their combined radiation and winds illuminate and sculpt the surrounding gas, revealing pillars, ridges, and ripples. None of this is decorative. It is a record of the forces at work: radiation pressure, gas pressure, gravity, and the magnetic tension that keeps filaments taut. Destruction and creation form a single loop here. Massive stars live fast and die in explosions that excavate holes in the interstellar medium. When several explode within a few million years, their overlapping shock fronts merge into superbubbles, tens to hundreds of light years across. Inside, the gas is hot and thin. Along the edges, compressed shells develop. Those shells can become the next generation of dense regions, breaking into clumps that fall back under gravity, starting the collapse that births new stars. The very event that ends one star's life can trigger the emergence of many more. In the statistics of star formation across a galaxy, these chains of cause and effect show up as clustered ages and nested shells. The scale of these bubbles matters. A single supernova might carve a cavity, but a cluster of massive stars can blow a tunnel through the disk. These are the chimneys that drive the galactic fountain. Hot gas from clustered explosions rises out of the thin disk into the halo, where the pressure drops and the gas expands. Over tens of millions of years, it cools, condenses into clouds, and falls back as a rain of neutral hydrogen. This circulation moves energy and metals from the crowded star-forming regions into the quieter outskirts, then back into the disk where future stars can use them. Without the fountain, the inner disk would hoard heavy elements and the outer regions would starve. With it, the galaxy shares. Chemistry turns this motion into meaning. Stars act as element factories. In their cores, hydrogen fuses into helium. In shells around the core, later stages build carbon, oxygen, neon, and magnesium. Massive stars push all the way to iron. When they explode, shock waves and neutron-rich ejecta assemble even heavier elements in milliseconds, from copper and silver to iodine and gold. Red giants shed carbon and nitrogen into space as slow winds. Supernovae spray iron and other metals into the surrounding gas. Every cycle increases the fraction of heavy elements in the interstellar medium. The dust that forms in cooling outflows locks in these elements as solids. Inside clouds, those grains become seeds that help molecules form on their surfaces and help new planets grow in disks around young stars. We see this activity across the spectrum. Invisible light, dust lanes cut across spiral arms, looking like shadows. In infrared, those same regions glow because dust warmed by starlight re-emits the energy it absorbs. Radio observations reveal cold hydrogen and carbon monoxide that trace the mass of molecular clouds. X-rays highlight hot bubbles and shock-heated gas. Together, these bands show a galaxy full of weather. And the patterns aren't random. Spiral arms, which are density waves, compress gas as it passes through them. Star formation spikes in those zones. As stars drift out of the arms, they carry the results with them, leaving trails of young clusters, hot bubbles, and fresh metals behind. The structure of a cloud reflects how it will collapse. Filaments are common, and their widths tend to cluster around 1/10 of a light year, set by the balance of turbulence, temperature, and magnetic support. Where filaments intersect, gravity wins quickly and forms clusters. In those clusters, feedback begins early. Radiation and winds from the first massive stars can shut down further collapse in the immediate neighborhood while compressing material a little farther away. That's how you get a hierarchy. Tiny cores within filaments, within larger clouds, within bubbles blown by clusters. Even the timescales vary widely. A hot bubble can last millions of years. A dense core can collapse into a star in a few 100,000. The radiation from an O-type star can clear a cavity in 1,000,000 years, while the cooling of halo gas in the fountain might take tens of millions before it falls back. These differences matter because they determine how efficiently gas turns into stars. Too much feedback too soon, and clouds disperse before they can form many suns. Too little, and the region collapses into a burst that uses up fuel quickly, leaving the area quiescent for a long time. The Milky Way sits in a middle regime where feedback regulates rather than extinguishes star formation. Magnetic fields add another control knob. They can slow collapse by channeling flows along field lines and by adding support against gravity. Observations show fields aligned with filaments and sweeping arcs above the galactic plane. In many regions, turbulence and the field strength balance gravity, building a threshold below which clumps disperse. Only where mass accumulates beyond that threshold do stars form. This keeps the interstellar medium from turning into stars all at once, stretching the process over billions of years and allowing multiple generations to contribute to the galaxy's chemical inventory. Within this network, H2 regions serve as signposts of fresh birth. Their sizes and brightness tell us about the power of the stars inside and the density of the gas around them. In some, the edges show bright rims where ionization fronts run into denser clumps. Those clumps can collapse after being compressed, a process known as triggered star formation. In others, the fronts break through and the region blows out, merging with larger cavities and adding to the superbubble complex. On smaller scales, planetary nebulae mark the gentler return of material from sun-like stars. As these stars exhaust their core fuel, they shed their outer layers. The exposed hot core emits ultraviolet light that makes the expanding shell glow. The shell carries carbon and other elements back into the medium, where grains can form and later become part of a protoplanetary disk. While less dramatic than supernovae, these events are numerous and significant, building up the elements needed for organic chemistry and rocky worlds. Now, step out of the mechanics for a moment and trace a single atom. An oxygen atom in your next breath may have formed in the core of a massive star, been expelled by a supernova into a hot bubble, drifted in the galactic halo as part of the fountain, cooled into a cloud, frozen onto a dust grain, then warmed and released as that grain moved into a disk around a young star. Inside that disk, it became part of a growing planet, was trapped in minerals, freed by geology, dissolved in an ocean, and finally taken up by life. The path is long, but it remains within this weather, gas to star to gas to star, with planets and bodies as temporary eddies in the flow. If this is the ocean you live in, then your body is a sample jar pulled from it. The carbon that shapes your cells, the nitrogen in your DNA, the iron carried by your blood, all pass through these storms. You are not outside the Milky Way's cycles, observing them from a safe shore. You are built from them, and as the galaxy continues its slow weather, new clouds will gather, new stars will light, new bubbles will rise, and the fountain will fall again, while some of your atoms begin their next long journey back into that quiet, restless sea. If the dark matter halo is the skeleton, and the disk is the organ system that circulates gas and stars, then the black hole is part of the heartbeat. Not the whole pulse, but a timing source. It is quiet enough that we sleep under its rule without worry, loud enough in its past to leave giant marks in the sky. Between those states lies the living galaxy, and if an engine and a skeleton exist, the space between must carry currents and storms of its own, a medium with its own cycles waiting to be traced. Breathe in and hold it for a moment. The oxygen moving through your lungs was not born with Earth. Those atoms came from a star that ran out of fuel, swelled, and cast its enriched layers into space. The iron riding through your bloodstream did not come from rocks alone. It was forged under crushing pressure when a massive star's core collapsed and a shock wave hurled the new metal across light years. Even the calcium in your bones traces back to a star near its end, shedding materials into the interstellar medium where future systems would gather them. With each breath and heartbeat, you are using matter that once burned as starlight. For a long time, that link stayed hidden. People saw stars as distant lights and Earth as separate ground. The bridge between them emerged only when astronomers learned to read spectra, those thin barcodes of color split by prisms and instruments. Lines missing here, lines bright there. Those signatures spelled out carbon, oxygen, silicon, and iron. They appeared not only in stellar atmospheres, but also in comets, meteorites, nebulae, and the sun's outer layers. The same patterns repeated in your blood chemistry and in the dust of interstellar clouds. That match revealed a single supply chain running from stellar cores to living cells. Life did not start apart from the Milky Way. It condensed from the debris field of stars that lived and died before the sun switched on. Think of how that supply chain works. A cold cloud of gas and dust drifts in the galactic disk, held together by gravity and shaded from harsh radiation. Over time, turbulence gathers clumps. Gravity tightens its grip. The cloud core collapses and spins. A protostar forms at the center, hot and dense, while a flat disk orbits around it. That disk holds grains made of carbon compounds and silicate minerals, microscopic seeds that stick together through static forces at first, then through gentle collisions. Pebbles grow into boulders. Boulders become kilometer-wide planetesimals. Gravity takes over, and these bodies merge in slow, violent encounters until a few large worlds claim the material near their orbits. What began as diffuse gas now exists as a star, planets, moons, and belts of debris. Inside the new star, the element factory runs on pressure and heat. At birth, the core starts with hydrogen. Fusion combines hydrogen into helium and releases energy that pushes back against gravity, keeping the star stable for long spans of time. When hydrogen dwindles, helium fuses into carbon and oxygen in hotter layers. In stars with higher mass, the sequence continues: carbon burning, neon burning, oxygen burning, silicon burning. Each stage sets up shells like onion layers, each shell fusing different elements. This assembly line builds the periodic table up to iron. Beyond iron, fusion no longer yields energy. It costs energy, and that creates a limit for peaceful stellar production. At that limit, massive stars reach a crisis. Their cores collapse in a fraction of a second. The shock rebounds. A supernova erupts. In that brief explosion, new paths for element making open. Neutrons flood the environment and latch onto atomic nuclei. Some add slowly in aging giant stars. Some add rapidly in supernovae, creating copper, silver, iodine, and gold. The shock wave tears the star apart and flings those elements into the surrounding space. That ejector mixes with the interstellar medium, seeding future clouds with more metals and molecules than the previous generation had. The galaxy's chemistry steps forward. Not all enrichment comes from explosions. Stars like the sun end more gently. As red giants, they dredge up carbon and S-process elements from deep layers and blow them outward in steady winds. Those winds form shells, cooling into dust grains that carry signatures of their parent star. Eventually, the core is left behind as a white dwarf, and the outflow becomes part of the diffuse material that will join other clouds later. The Milky Way is full of those contributions. supernovae for rapid neutron captures, giant star winds for slow ones, and steady fusion output for the mid-range elements. This constant recycling changed the raw ingredients available for planet building. Early in the galaxy's history, stars formed from almost pure hydrogen and helium. Those first generations left behind little solid material for planets. Over billions of years, their deaths raised the metallicity of the gas. By the time the Sun formed about 4.6 billion years ago, the local cloud was rich enough in heavy elements to build rocky worlds. The protoplanetary disk contained silicates, ices, organics, and metals. That mix allowed small dust grains to stick, ice-coated pebbles to collide, and metal-rich cores to grow. The Earth's iron core and silicate mantle speak to that inheritance. So do the carbon chains discovered in meteorites, preserved since the earliest days of the solar system. Those meteorites also carry pre-solar grains, tiny mineral fragments that predate the Sun. Their isotopic ratios point to origins in different kinds of stars, from red giants to supernova ejecta. They survived the turbulent collapse of the solar nebula and became embedded in primitive rocks. When scientists dissolve the meteorites and isolate those grains, they read the nucleosynthesis history encoded in their atoms. The same patterns tie to what telescopes see in stellar spectra across the galaxy. The match is not an abstract idea. It is a measurable link between a distant star's life and the minerals in your teeth. The route from cloud to cell continues through planetary assembly. As Earth formed, heat from impacts and radioactive decay melted parts of the young planet. Heavy elements sank to the core. Lighter silicates floated upward to build the crust. Volcanoes released gases. Water arrived through a mix of outgassing and icy bodies from the outer system. Carbon-bearing molecules reached the surface, carried inside rocks and dust. Some made in interstellar clouds, some formed in the protoplanetary disk. Over time, chemistry on the surface and in the oceans built complex structures that could store and replicate information. Those pathways took advantage of the periodic table the galaxy supplied. Without that table's gradual enrichment, no stable land masses, no oxygen-carrying blood, no ATP bonds, no phosphate backbones. You can track the stages of this supply chain in the composition of living things today. Oxygen fills your lungs because it bonds easily and releases energy when combined with carbon-based molecules. Iron binds in hemoglobin because it can toggle between oxidation states and carry oxygen efficiently. Calcium forms tough lattices in bone because of its charge and size, making strong mineral scaffolds when paired with phosphate. These choices of nature are choices of chemistry, and those chemistries exist because stars ran their cycles many times before the Sun formed. Biology is downstream from nucleosynthesis. This dependence sets a clock on complexity. You need heavy elements for rocky planets and for the molecules that life uses. But heavy elements do not appear quickly. They accumulate through many rounds of star birth and star death. Early galaxies may form stars rapidly, but until supernovae and giant star winds enrich the clouds, you cannot build Earth-like worlds in abundance. The Milky Way took billions of years to climb from low metallicity to the levels found near the Sun's orbit today. That timing matches the ages of exoplanet systems where rocky planets show up more often around stars with higher metal content. It also explains why life here appeared late compared to the age of the universe. Complexity waited for the right inventory. The Sun's own classification reflects that timing. It belongs to a metal-rich population formed after many generations had lived and died. Its birth cloud already held the carbon needed for organic chemistry, the silicon for rock, the iron for cores, and traces of heavier elements made in violent stellar ends. The solar nebula was not pristine. It was second-hand material, well mixed, full of dust that had already toured through other stars. The fact that you can drink water, metabolize sugars, and repair DNA comes from that prior history. Your body uses a kit assembled by the galaxy over eons. Spiral arms matter to this story. They compress gas and trigger star formation. Massive stars form there, live short lives, and return their products quickly to space. That keeps the cycle moving. But the arms are also busy places where radiation and shocks can strip atmospheres. The sun orbits in a quieter spur between major arms. That location may have helped Earth keep its air and water long enough for life to develop. It also means our local clouds received a steady supply of enriched material without being overwhelmed by frequent destructive events. The balance of enrichment and calm appears in the rock record and in fossil chemistry. Even now, the cycle continues above your head. New stars switch on in nebulae. Others swell and cast off shells. Some end in supernovae that send shock waves through nearby gas, stirring it and setting up the next generation of births. Dust grains form in outflows, carry complex organics, and drift into cold clouds. Over time, those clouds will collapse and collapse again, feeding formation after formation. The interstellar medium acts as the galaxy's shared bloodstream, moving raw materials between sites of creation and sites of destruction. All of this reduces to a clear requirement. Life like ours needs a certain chart of elements and stable conditions for them to assemble. That chart exists because the Milky Way has worked its forges for billions of years. A younger galaxy with fewer heavy elements would not have enough solid material for many rocky planets or enough chemistry for complex cells. A region with frequent explosions would bathe planets in radiation and strip atmospheres before life could take hold. The Earth sits in a window that opened only after generations of stars loaded the local space with the right inventory. Your breath today runs on oxygen forged in earlier suns. Your heartbeat relies on iron that came from a dying star's last burst. Your skeleton stores the memory of red giants. Hold that thought as you exhale. If life draws from this exact chemical heritage and from a recycling engine that takes billions of years, then our galaxy is not uniformly welcoming. Some neighborhoods provide the ingredients and the calm. Others are rich but hazardous, or calm but starved. The Milky Way has quiet corners and stormy avenues, and where you find yourself on that map could decide whether chemistry gets long enough to wake up. Step inward toward the galactic core, and the neighborhood changes fast. Stars pack in tight, separated by only a fraction of a light year in places. Ultraviolet light and X-rays fill the environment as supernova shock fronts run through the region like weather fronts that never end. Gravity funnels gas toward the center, feeding outbursts that heat and stir the medium. In a place like that, a newborn atmosphere would strip away under constant radiation. Even if planets formed, nearby blasts would shower them with cosmic rays and ejecta. A world attempting life has to keep its molecules intact long enough to try, and in the inner few thousand light years, the sky keeps resetting the clock. Walk outward toward the disk's edge, and another problem emerges. The radiation quiets, but the material grows thin and primitive. Gas clouds carry fewer heavy elements, the ingredients for rock and water-bearing minerals. Dust grains form less efficiently. Planet building slows. Disks around young stars remain poor in iron, silicon, oxygen-rich ices. A small set of worlds will still assemble, but the odds shrink. You can have safety and emptiness, or danger and richness. Between these extremes lies a narrow ring where both demands meet in balance. That ring is the galactic habitable zone. It is not a line you could draw with a pen, but a band where conditions overlap in our favor. Move through it and metallicity stays high enough for rocky planets to build its scale, while the bombardment of high-energy events remains low enough for atmospheres to persist. The zone sits at roughly 23,000 to 30,000 light-years from the center in our galaxy. Inside the band, star birth continues without constant catastrophe. Outside, the recipe thins out. The band is not fixed. It changes slowly as the disk enriches and gas flows, but for now, it marks the long corridor where complex chemistry gets the time it needs. Our system lives inside this corridor, not simply at the right radius, but also in a quieter traffic lane. The Sun rides in the Orion Spur, a minor branch that threads between the Perseus and Sagittarius arms. Those major arms are busy regions. Gas compresses there, massive stars flare and die, and supernovae seed energy into the medium. They are construction zones. The spur avoids the worst congestion while still sampling the flow of fresh material along the disk. That gap between arms reduces the chances of a nearby massive star exploding within the window that matters for life on a young planet. Spiral structure adds another layer. The arms move through the disk as patterns, not rigid objects. They act like slow-moving traffic waves where matter gathers and then disperses. The speed of those waves matters because crossing them often exposes systems to denser clouds, brighter neighbors, and more frequent supernovae. The Sun orbits at nearly the same angular speed as the arm pattern, near the co-rotation radius. That reduces how often we pass through major arms. Fewer crossings mean fewer hazardous episodes. It does not make the environment safe in any absolute sense. It makes it calmer on average over hundreds of millions of years, which is the timescale biology demands. Look again at the inner disk to see why this fine-tuning matters. High stellar density increases the odds of close stellar passages. A flyby can perturb comet reservoirs and trigger heavy bombardment, or tug on outer planets and destabilize orbits. In the core adjacent regions, these encounters become more likely. Combine that with stronger radiation fields and the periodic activity near the center, and you get a neighborhood that resets planetary clocks often. Chemistry can still proceed. Planets can still form. But the window for long-term surface habitability narrows. Head to the outskirts and the hazards change. You dodge most outbursts, but many stars there form from gas that never saw enough previous generations of enrichment. Without sufficient metals, protoplanetary disks hold fewer solid grains. Rocky cores form slowly and often stay small. Giant planets that protect inner worlds by absorbing comets may fail to form as well. A planet might still host a subsurface ocean under ice, warmed by internal heat. But stable continents, thick atmospheres, and complex surface chemistry need heavier elements in generous supply. The outer disk struggles to deliver them. The habitable zone brings all of this into a single, practical frame. You need iron for a magnetic core. You need silicon for rock, oxygen for water, and trace elements for biochemistry. You also need time without catastrophic sterilization. The band, at roughly 23,000 to 30,000 light-years, provides that blend. It is not uniform. Pockets within it run hot with star birth, while others drift quiet. Stellar migration will move systems inward or outward across hundreds of millions of years. But statistically, this ring places more systems in the long patience that complexity requires. The Sun's specific lane adds a layer of fortune. The Orion Spur sits between those two major arms, so we avoid constant immersion in star-forming chaos. We still encounter clouds and associations, but not with the frequency that grinds atmosphere-bearing planets down. The lower background flux of cosmic rays helps keep atmospheric chemistry stable enough for ozone to persist and for DNA-level structures to avoid excessive damage. The lower density also reduces gravitational interference from neighbors. A planetary system has more room to keep its architecture intact. Those dynamics shift with the arm pattern. The co-rotation neighborhood means the Sun is not slamming through arms on short intervals. It drifts alongside the wave crest for long stretches. That reduces the rate at which we encounter dense molecular clouds that could perturb comet reservoirs or trigger extended climate changes. Matches like this between orbital speed and pattern speed are not magical safeguards, but they tilt probabilities. Over billions of years, small tilts add up. The city metaphor helps hold this all together. The downtown core is bright, crowded, and volatile. Work gets done there. Stars form, gas flows, energy moves, but the noise level is high. The spiral arms are the highways and construction zones, busy with the constant churn of building and demolition. The suburbs out here offer fewer close calls and more predictable rhythms. Utilities still run. Supplies still arrive. But there is space to grow without the daily threat of a demolition crew next door. That quiet gives a biosphere time to experiment. As with any city, zoning shifts, the arm pattern drifts. The bar in the center can change the flow of gas, redistributing star birth across the disk. Migrating stars carry their planets across districts. A system that lives in the band today may not in a billion years. Conversely, some that start in harsher zones can wander into quieter lanes. Habitability is not a fixed property, but a probability that changes with time. Our moment happens to sit at a favorable point in that shifting map. Cosmic rays add a subtle but important pressure across these regions. Near the inner disk, their flux grows, driving atmospheric loss and chemistry changes. Far out, the flux drops, but so does element supply. In between, the average levels land within tolerances that atmospheres can manage over long timescales, especially when a planet carries a magnetic field and recycles its crust through tectonics. Those planetary defenses emerge from the same heavy elements that the zone supplies. It all links back to enrichment and restraint, delivered together in just the right dose. Even the cadence of nearby supernovae follows this map. In the arms, massive stars die more often and sooner, flooding space with particles and shock waves. Between arms, the rate drops. The sun's route threads a path that minimizes these direct hits. It has not been free of events. The geological record hints at past encounters with supernova debris, but the intervals appear long enough to avoid sustained damage to the biosphere. That is the difference between setbacks and erasure. None of this guarantees habitability. It stacks the deck. It means many systems in the ring will still miss the target because of local events, planet formation quirks, or later orbital disruptions. It also means some systems outside the ring will beat the odds. But if you were betting on where long-lived, surface-dwelling life could take hold in a spiral galaxy like ours, you would place your chips on the quiet bands between the busiest lanes, at the distances where the chemistry is rich and the sky is less likely to lash out. That raises a quiet question in the dark. If conditions fall into this ring only across a thin span, and if the safest lanes between arms are as sparse as ours, then how many neighborhoods across the disk share this luck at the same time? A few thousand? A few million? Spread over 100,000 light years, with time stretching into billions of years, even a small fraction becomes a large number. Yet the spaces between those numbers are vast. And what happens when the pattern changes under us? Spiral arms shift. The bar may strengthen or weaken. The sun drifts relative to the wave over tens of millions of years. A lane that stays quiet for a while can grow noisier as we slide into a region dense with gas. A world that enjoyed a long calm may face new traffic and brighter neighbors. The map of safety moves, and stars move across the map. The question lingers as the disk turns. How many worlds keep their calm long enough to wake up and listen, and how many fall silent when the neighborhood changes its mind? Tilt your gaze away from the bright river of the Milky Way and into the dim outskirts where the light thins. Out there, the sky stops being smooth. Faint chains of stars arc in long, careful curves, and tight swarms of ancient suns hang like cold embers. Globular clusters mark the territory like mileposts. Most eyes slide over them, but they carry records the main disk does not. They drift through the halo with the confidence of old travelers, and their motions, when measured precisely, write out the story of broken galaxies that left their shapes behind and became these thin threads across the dark. The night became a map when measurement caught up with it. With astrometry precise enough to spot a hair swaying at the moon's distance, the sky fractured into detail. What looked like scattered points began to move in patterns. The smooth background split into scars and streams, tracks of gravity's pull from long ago. Velocities that once blurred into averages resolved into families. Some stars run ahead, some lag behind, some cut sideways through the swarm. That precision exposes wounds, long tidal tails, splayed debris, and overlapping arcs that show where the Milky Way pulled smaller companions apart and spread their stars over vast paths. This is how the forensics work. Stars born together inherit the same chemical mix from their parent cloud. They also share an initial trajectory. Even after disruption, those traits persist. So astronomers sort the sky by motion and composition, looking for clusters of agreement in a sea of differences. A group with the same iron abundance, the same magnesium ratio, the same path through the halo, tells you they started as one thing. They may now span half the sky, but they still move like relatives passing each other in a crowded station. That's the clue that turns a random sprinkling of dots into the surviving shape of a galaxy that no longer exists as a single object. Follow one of these trails, and you find the ongoing meal in our own sky. The Sagittarius dwarf galaxy is stretched into loops that wrap around the Milky Way more than once. Its core is dim, but its stars line up into arcs that cross the constellations in ways only careful measurement reveals. Each pass tears away more mass. Each lap leaves new debris behind. The galaxy is being peeled, star by tides too large to feel and too slow to notice without long patience. Those loops do not dissolve quickly, so they persist as guides, showing where the Milky Way's gravity pulled and when. Go deeper, and you hit the event that rattled the early Milky Way. A large dwarf galaxy plunged straight into the young disk billions of years ago. The remains of that crash travel today on chaotic orbits that cut through the plane, many moving backward with respect to the main rotation. Their paths look like thrown gravel rather than calm rings. That population dominates the inner halo. In the chemistry of those stars and in their motion, you see the outline of a head-on merger that puffed up the disk, thickened it, and left debris on energetic, elongated orbits. Not every stream comes from a single clean event. Some arrived along different angles, slower or faster, and left debris that we only now separate from the background. There is a set of stars on strongly retrograde paths with metallicities that match each other more than they match the disk. Another stream slices at a steeper tilt, winding around the halo with a rhythm distinct from the rest. Their names are shorthand for entire histories, but what matters is that their motions and chemistry agree, and that agreement says they were once coherent systems that the Milky Way's tides took apart. The halo reads like layers in exposed rock. Outer regions hold stars with fewer heavy elements, signaling formation in small, early systems that did not enrich themselves much before being consumed. Inner regions hold a mix. Some old, some slightly younger, some from our disk heated into higher, rounder orbits by ancient encounters. By placing composition against motion, the timeline emerges. You can tell which events came first, which stretched longest, and which left marks in the disk itself. The thick discus stars, for instance, carry higher alpha element ratios in orbits that rise above the plane, pointing to a time of active, rapid star formation and dynamical heating consistent with a major merger's aftershocks. Across the sky, these thin rivers create a different way to view the Milky Way. It is less a solitary spiral and more a compilation that kept its shape only because gravity smoothed the chaos over long periods. Streams outline the orbits that past dwarfs traced as they fell in. Breaks and kinks show where they crossed the disk and lost energy. Overdensities mark where compressed tides helped clusters survive. The arcs are not random decoration. They are the framework drawn by past intruders. Watch how stars share habits. A group comes with similar iron content and the same odd calcium to iron balance. They also travel together on a tilted plane that intersects the disk near one of the spiral arm tangencies. Those coincidences are almost impossible to fake at scale. The match points to a common gas cloud with a specific enrichment history, which means a single galaxy or cluster produced them. The Milky Way has scattered them widely, but their shared origin remains caught in their spectra and in the way they swing around the center. Even the retrograde groups tell you something clear. If a set of stars moves opposite to the disk, it did not form inside that disk. It had to be captured. Over time, interactions spread their orbits and mixed their directions a little, but the original sign of their approach survives. That backward motion is a quiet confession. It says the halo is full of imports. Consider how far this reaches. Some of the light hitting your eyes began in systems that had different centers, different clocks for star formation, and different distributions of elements. When those systems fell into the Milky Way's pool, they did not vanish. They became part of the halo and part of the disk's outskirts. Their clusters now swing high above and below the plane. Their orphaned streams wind around us. The night sky is not a single city. It is a metro area built from towns absorbed long ago. The method that exposes this, at its core, is simple but demanding. Measure a star's position and motion with great precision. Split its light to find the imprint of elements in its atmosphere. Combine the two. If a set of distant points shares both a path and a chemical recipe, then they are a family. If that family crosses the sky in an arc and its velocities line up along the same curve, then you have a stream. If the stream's composition is poorer and heavy elements than the disk's, then it likely came from a small galaxy or cluster. Piece by piece, the map fills. Take the ongoing stream from Sagittarius. It wraps the sky in multiple loops offset by tiny differences in speed and angle, because not every star was stripped at the same time. The outermost loop formed earlier and has spread farther. Inner loops are younger, tighter, and closer to the remnant. Overlay the star's velocities and you can trace where each loop crosses the disk, where friction with the denser regions bled energy, and where the debris will go next. Now line up the debris from the older, larger impact that seeded the inner halo. Those stars pile up at a center, where their orbits slow, creating clumps in position and speed that stand out in data. Their chemical pattern points to a system that formed stars quickly and then stopped, leaving a distinct ratio of alpha elements to iron. That chemistry matches the sort of dwarf galaxy that could carry enough mass to punch into the young Milky Way and restructure it. The agreement between motion and composition strengthens the case until the event is not just a theory, but a coherent explanation for features we still see. The halo's streams point out that our galaxy's history is paced by meals, not just by internal growth. Each stream is a path through which mass arrived and settled. Each one added stars and dark matter to the mix, changing how the disk evolved. They are both footprints and ingredients. If you trace them all, you outline the roots along which the Milky Way grew. There is a quiet feeling that comes with this realization. The stars overhead are not all native. Some glide along lanes set by collisions and captures. Their light carries the story of where they were made, and that story often begins outside the Milky Way's boundaries. The night becomes a museum where the exhibits move in slow orbits, and the labels are written in velocities and elemental ratios rather than words. Not every fragment ends up part of the collection. Some encounters fling stars out at such speeds that they leave the galaxy behind. Tidal forces can catapult debris over the escape limit. A close pass near massive structures can trade energy in a way that sends stars outward on open trajectories. Those exiles do not return. They carry their chemical tags and their origin stories into deep space, crossing the dark between groups with no home left to circle. They start as loyal partners, circling each other like well-behaved dancers until gravity finds a way to break the pair. Near the galactic center, a binary star wanders too close to the supermassive black hole. In a fraction of a second, the pair is torn apart. One star is trapped, the other is fired outward at thousands of kilometers per second, so fast that not even the Milky Way can hold it. These are hypervelocity stars. They cut through the halo on escape trajectories, rising far above the disk, their paths tilted and lonely. Some will pass the outskirts of our dark matter halo and keep going, their fuel slowly burning as they cross the empty lanes between galaxies for hundreds of millions of years. They are rare, but they are real departures, proof that even in a gravity-bound system, release can happen with a single, violent encounter. Not all runaways come from the core. Close interactions in dense clusters throw stars to extreme speeds too, especially when massive stars trade partners or collide. The result is the same: a star on a one-way route, climbing the galaxy's gravitational well, stretching its orbit from the inner disk to the far halo and then beyond. As they leave, these exiles pull their own comet clouds and any trailing debris into elongated paths, reshaping the small systems that tried to follow them. From our vantage point, they appear as high-speed outliers with odd chemical blends and sharp, slanted motions that defy the smooth rotation of the disk. Now shift from blazing suns to silent worlds. Rogue planets are born in chaos, not in light. In young systems, giant planets migrate inward and outward, scattering smaller worlds and asteroids like gravel. A near pass with a neighbor star can twist a planet's orbit into a slingshot. Over time, enough nudges add up. Gravity lets go. The planet leaves. With no star to warm it, the surface falls into permanent night. But the story does not end in frozen rock. Some worlds carry heat inside. Slow radioactive decay in their cores can keep subsurface oceans liquid for billions of years beneath ice shells. A thick atmosphere of hydrogen, if it survived ejection, could trap heat and keep the interior warm. These wanderers are nearly invisible, detectable only when they briefly pass in front of a distant star or when a microlensing event betrays their presence as their gravity bends light from behind. The counts are uncertain, but the numbers may be staggering, with many times more rogue worlds than stars. That means a dark archipelago of planets drifting between the arms, with or without frozen seas, drifting without a dawn. The quiet part is that our own family history started in a place built for such chaos. Stars form in clusters, not alone. A single collapsing cloud gives rise to hundreds or thousands of suns, packed tight enough that close encounters are common. Protoplanetary disks brush past each other. Ultraviolet radiation from massive newborn stars scours the gas around their neighbors. Gravity shuffles orbits like cards. Within a few million years, that nursery disperses. Tides from the Milky Way tug at the cluster. Nearby molecular clouds pull stars away. What was once a tight-knit community smears into the disk until nothing but a faint moving group remains, and then even that dissolves. The Sun almost certainly formed in such a nursery. Its siblings drift now as strangers, some older-looking from slower rotation, some enriched by the same ancient supernova that seeded our birth cloud with aluminum and iron. They follow paths scattered across the disk and halo, the diaspora of one long-vanished cluster. To find them, astronomers read two kinds of evidence. Motion first. Stars born together start with similar velocities, and while the galaxy stirs them over time, patterns remain. A shared drift here, a matched eccentricity there. Then chemistry. A star's light contains absorption lines from elements in its atmosphere. The ratios of iron to oxygen, magnesium to silicon, sodium to aluminum form a signature. Stars born from the same cloud tend to carry the same blend. Combine motion and chemistry, and you can flag candidates, possible solar siblings mixed into the background. A few stars have emerged as promising matches in both age and composition, though certainty is hard. After billions of years, the trail blurs. Many families erase themselves completely, their members stretched into streams too faint to pick out from the city of the disk. Cluster dissolution sets the tempo. Gravity from the rest of the galaxy presses on a cluster's edge, and interactions inside push stars outward. One by one, they peel off, losing the protective bubble that a crowded cluster can offer. For planets, that shift matters. Early on, in the thick of the nursery, a close flyby can tilt orbits, hurl comets inward, or eject a small world entirely. Later, when a star moves to the suburbs, the space between neighbors grows. The odds of a disruptive pass drop with time. Our solar system likely survived its most dangerous decades while still cocooned in gas and dust, then left the nursery with its architecture mostly intact. Most families are not so lucky. Many stars leave with rearranged systems, new orbits, bodies missing. The census of rogue planets may be their legacy. Hypervelocity stars and rogue planets sit at the extreme ends of this process. One begins as a privileged partner, flung into exile by a brush with the central black hole or by rough play in a cluster. The other begins as a passenger, lost to the shuffle of early planetary dynamics or a stray encounter with a neighbor. Both remind us that the galaxy is not a quiet carousel. It has lanes and hazards, detours and exits. Even in the outer disk, a passing star can sweep through the Oort cloud, dislodging comets into long, slow arcs toward the inner system. The further in you go, the more often those passes occur. In the inner few thousand light years, stars crowd so tightly that planetary systems live under constant threat of gravitational interference. Disks are truncated. Orbits are pumped into eccentric loops. Worlds are tossed away like sparks. That contrast defines our fortune. We live in a minor spur, not a major arm. Our neighborhood is sparse enough that the night sky stays calm for spans long enough to build continents and oxygenate seas. The sun's orbit places it near the co-rotation radius, where the spiral pattern overtakes and lags by nearly the same speed, reducing the number of times we cross dense arm segments. Fewer crossings mean fewer giant molecular clouds to disturb our path, and fewer massive star clusters to bathe us in radiation. Out here, supernovae are rarer and farther. Out here, the background hazards are present but manageable. The pinball machine still plays, but the bumpers sit farther apart. Meanwhile, the inner galaxy tells a different story. Near the Barren Bulge, stars pass each other at closer distances. Planetary systems feel tidal tugs that a suburb like ours never experiences. A few close passes over a billion years can lift a planet's orbit until it grazes others, triggering cascades that eject small worlds and flood inner systems with comets. The outcomes vary. Sometimes you get a reset that sterilizes a world for a while. Sometimes you launch a planet into the halo on a lonely path. The border between stability and mayhem is not sharp. It is a gradient written in stellar density and relative speed. Even the exiles leave signatures behind. A hypervelocity star exiting the disk can carry a bow wave of interstellar gas if it plows fast enough, briefly lighting a faint arc. A rogue planet moving through a patch of dust might collect a thin atmosphere of volatiles only to lose it again. These signs are rare and transient, and the distances are unforgiving. Most of the time, the wanderers pass silent and undetected. We learn they exist because the galaxy offers just enough gravity and chance alignment for their paths to bend starlight in measurable ways. Catch a microlensing event from a starless mass lasting hours rather than days, and you have evidence of a free-floating planet. Track a star's speed and direction to absurd precision and find it racing faster than escape velocity, and you have a hypervelocity candidate. All this motion helps redraw the map of where we are safe and where we are exposed. Our suburbs feel quiet because the galaxy's traffic patterns keep the worst pileups away from us most of the time. But the map is not fixed. Over tens of millions of years, the sun bobs above and below the disk, shifts inward and outward a little, and passes through different neighborhoods. In a few 100 million years, we will drift into new alignments, cross new arms, and see hazard rates rise and fall. Stability is a time scale, not a guarantee. There is a larger lesson sitting behind the exiles and the lost families. If a star can escape a galaxy, if a planet can wander between suns, then a galaxy is not a closed box. It trades mass with its surroundings. It loses some, it gains some. It belongs to a group, and that group belongs to a flow. Our Milky Way is held with its neighbors in a loose cluster moving along the strands of the cosmic web. The same gravity that punches stars out of the disk pulls entire galaxies toward one another across millions of light years. The runaways from our system may one day travel through the outskirts of another, and theirs may pass silently through ours. The fabric that binds the local group allows even its smallest members to roam, which means the next part of the story steps beyond any single spiral and follows the shared motion of all of them together. Step back until the Milky Way is no longer a sky-wide band, but a single smear of light. It sits in a loose neighborhood of more than 50 galaxies, all held together by gravity across a span of over 10 million light years. From this distance, our home is not an isolated spiral. It is one island among many in a quiet archipelago, drifting in a shared tide. Each island pulls on the others. Each orbit is slow enough to feel still, yet steady enough to rewrite the map over billions of years. The space between them looks empty, but their motions say otherwise. Threads of faint gas, scattered dwarfs, and long histories of past tugs link these objects into one family. In that family, one member sets the tempo. Andromeda carries roughly twice the mass of the Milky Way, moves toward us at about 110 kilometers per second. You can find it on a clear night as a pale oval wider than the full moon, though its light is thin and easy to miss. It is not a visitor that will swing past and vanish. It is inbound, already inside the same gravitational well we share. The fact that most people never notice it does not change the scale. The largest galaxy in our group is on a path that leads straight through our future, and the line has been drawn for a very long time. The rest of the local group does not sit idle while the two giants approach. Dwarf galaxies orbit like flocks, keeping loose formation. Some are bright enough to earn names and stories. The large and small Magellanic Clouds trail to our south, their arcs of gas stretched into a long ribbon known as the Magellanic Stream. That stream is a record of past pulls and near passes, a sign that their first close encounter with the Milky Way may be recent in cosmic terms. Others, like Leo Phaon or Draco, glow with old, metal-poor stars that keep time with early cosmic conditions. And then there are the ultra-faint companions, objects so dim that they hide in the noise of the night. Each carries its own chemical accent, a marker of where and how its stars formed before the group shaped them. Gravity writes in slow strokes, and the group's history is readable in those arcs. The Milky Way's outer halo bears scars from earlier meals and near misses. Andromeda holds its own retinue of dwarfs that it has shuffled and stripped. None of these paths are straight lines. The galaxies weave through each other's pull, trade energy, and settle into new tracks. A dwarf that falls in close can lose its gas, stretch into a stream, and leave its stars behind as a faint, elongated cloud. Another may skate the edge and keep its shape for another orbit. Over time, the heaviest members sit near the center of the common gravity well. The rest form a loose gradient outward, like small boats circling a pair of large ships. Pull the camera farther still, and the local group shrinks to a dot among many. It lives inside the Virgo supercluster, which itself falls within a larger flow known as Laniakea. These are not structures in the way a city block is a structure. They are patterns of clustered groups and clusters of clusters, following the deeper contours of the cosmic web. Mass is not spread evenly. It gathers into filaments and knots, leaving wide gaps between. The local group moves along one of those lanes, its course bending with the wider pull. Beyond even that, observations point to a broad region that tugs at much of the nearby universe, the Great Attractor, turning local motions into part of a much larger drift. This hierarchy matters because it sets the stage for what happens next. The Milky Way and Andromeda are not only closing the distance because they want to, they are embedded in a net that guides their approach. Their dark matter halos, far larger than their starlight suggests, already overlap in the most delicate way. The first contact is not a crash of stars, it is a merging of invisible mass. As those halos sink into each other, the two disks will feel changing tides. Outermost stars will adjust their routes, long-period companions will switch allegiance, and gas streams will start to warp and twist into new shapes. On the sky, the change arrives quietly at first. Andromeda grows slowly brighter over many generations. Its spiral features resolve. Faint streams become more obvious. Then come the passes. The two galaxies move through each other, not once, but several times. They trade angular momentum. Stars shift into new orbits. Some are flung to great distances, forming broad shells and long tails that drape around the merging pair. The spiral arms, which rely on stable patterns in the disk, lose coherence as the gravitational field changes. The neat lanes of star formation smear out. Over a few billion years, the system settles into a rounder, smoother form. Astronomers call the likely result Milky Way, an elliptical giant with a diffuse envelope and a central body that holds the mixed legacy of both parents. This is not a story of explosions filling the sky. The distances between stars are so large that direct collisions remain rare. The drama plays out in orbits and distributions, not in widespread impact. Gas clouds feel it more strongly. They compress where tides squeeze them and shear where the field stretches them. You would see episodes of bright star formation sparked by those squeezes, then lulls as gas is heated and dispersed. The central black holes would meet and spiral inward through a background of stars, eventually merging and sending a brief pulse of gravitational waves through the new galaxy's body. The shape we know today, the tidy two-armed spiral with a bar and distinct suburbs, would fade into the memory of the local group's early age. Around this central event, the smaller members do what they have always done. They are captured, disrupted, or left to wander at the edges. The Magellanic Clouds, with their stream already in place, likely feed gas and stars into the main body during the dance. Ultrafaints contribute tiny trickles of ancient light, each drop changing the chemistry and kinematics in small ways. Some dwarfs, bound to Andromeda, now will switch and become satellites of the new combined galaxy. Others will be slung outward, becoming rare intergroup wanderers that carry fossil records of the merger's tides. The broader web continues to frame the scene. The local group's relative isolation within its part of Laniakea gives the merger room to unfold without another giant immediately disturbing it. Over greater spans of time, gravitational flows will bring other groups closer. For now, the important motion is internal. Two large spirals settling along a count. The physics that guide it are the same ones that shape galaxy histories everywhere. Halos gather. Disks grow and warp. Satellites feed their hosts, then pairs meet and become one, passing from the spiral stage to the elliptical stage when their gas is used up or heated beyond easy cooling. Back on Earth, the change will rewrite the constellations, then the very idea of constellations. Long before the final coalescence, the night will carry two bright cores, lanes of stars stretched between, and clouds of new clusters lighting the bridges. When the arms dissolve, the sky will lose its familiar sweep of the Milky Way and gain a bandless glow. After the system relaxes, future observers will see a large, smooth galaxy dominating their sky, its halo blending into a broad, faint background. Through all of this, the timing remains forgiving. The approach takes billions of years. Civilizations can rise and fall many times before the sun sets behind the first passage. The slow pace does not make the event trivial. It allows the underlying order to show through. The local group is built to evolve in this way because gravity favors merger. Small things join to make larger ones. Large ones gather into still larger assemblies. The result is not destruction for the sake of it, but a reshaping of where stars live, how gas moves, and what paths are possible. It helps to remember that our current view is temporary. The local group was quieter once, and it will be quieter again in a different form. We use names to fix it. Milky Way, Andromeda, Magellanic Clouds. But the labels sit on motions that never stop. The faint oval next to our constellations is not a distant curiosity. It is part of our system's future outline. The halos are already in contact. The arcs in the outskirts already curve toward their shared center. Like all structures in the web, this one tends toward fewer, larger nodes. So the night sky, you know, is a phase rather than a statement. It is the current arrangement of a moving family. And the most striking part of that family lives on a collision path that favors blending, not breaking. The spiral pattern we grew up under has a shelf life measured in orbits and tides. What comes next is not a crash, but a long, quiet exchange that ends with a single, larger home. Which means that when you look up now, you are seeing a snapshot just before the long rearrangement begins, and the next chapter waits with its own strange geometry. The approach has already started. Two halos of dark matter move toward each other across billions of years, drawing their galaxies with them the way a tide pulls ships that cannot anchor. There is no switch to flip, no brake to press. The path tightens slowly at first, and then inevitably as gravity does what it always does. It adds, it gathers, it closes distances until orbits weave together. The number to hold in mind is not a date on a calendar, but a span, about 4.5 billion years until the first deep pass. The physics is plain. Once the separation shrinks below a threshold where their halos overlap strongly, mutual gravity locks the dance, and every subsequent pass steals more energy from their motion until the pair cannot escape each other again. Long before any physical interlacing, the night sky changes. A faint smear, easy to ignore, grows brighter. It stretches into an oval you can point to without a telescope. It spreads its length until it rivals the moon's width many times over, but remains ghostly, like breath on glass. Across millions of years, the smear becomes a band, a river of unresolved stars, turning from a distant object into a second skyline. Our own Milky Way's arch meets that widening ribbon, and they share the darkness. The stars do not blur together from one night to the next. They accumulate presence. When the first pass arrives, that river's detail sharpens into knots, star-forming regions lighting up, while long dust lanes become visible to any eye that can see. The sky turns into a double exposure, two spirals laid across each other, each tilted, each rotating on its own clock. Constellations break their old context. Familiar patterns keep their shapes, but no longer rule the view. A collision sounds violent, but here the violence is statistical. Space leaves room. The span between typical stars is so large that direct star-to-star hits are rare, even when two disks interpenetrate. What you get instead is a rerouting of trajectories. Gravity acts like syrup on glass marbles, changing paths without cracks or sparks. As the galaxies pass through, tidal forces draw out streamers of stars that look like arms pulled long. Whole stellar neighborhoods find themselves on new, wider or narrower orbits. Clouds of gas feel dragged from collisions with other gas clouds and slow, while the stars sail on, almost untouched. The old orbits that once circled a single center now precess around two, then one again, as the pair trade momentum with tidal tails acting as brakes. The first pass does not end the story. It sets up the second. After the deep approach, both galaxies fly apart somewhat, but not enough to escape. Their halos and tidal debris have stolen orbital energy. They arc out, pause over a span of hundreds of millions of years, then fall back in. With each return, the centers come closer, the tails longer, the structure less like disks and more like a tangled bridge of stars. Gas collides and compresses. Star formation flares where clouds meet and squeeze. The glow of newborn star clusters paints edges of dust with pale light. Supernovae begin to dot the new clusters after a few million years, feeding turbulence into the already stirred medium. At the heart of each galaxy sits a massive black hole. Ours carries about 4 million solar masses. Andromeda's holds far more. They do not head straight toward each other at once. They follow their host cores through the messy dance. As the larger structures merge, dynamical friction makes the black holes sink toward the new common center. Stars scatter off their combined gravity, dumping kinetic energy and letting the pair tighten their orbit. Eventually, they form a bound binary deep inside the merged core. Their separation shrinks further through 3 avenues: continued interactions with stars, torques from surrounding gas, and, at the smallest distances, the emission of gravitational waves. When they finally coalesce, the merger releases a clean pulse of space-time ripples. No flash, no sound, but a ringing in gravity itself that travels outward. The recoil kick from the merger could shift the new black hole within its galaxy, but for a galaxy of this size, it will remain embedded in the center, becoming the anchor of a new gravitational order. As this central drama unfolds, the larger shape evolves. Spiral arms thrive on ordered rotation and density waves in a disk. Mergers scramble that order. The neat pinwheels unwind, stretched by tides and dissolved by random motions. Gas flows toward the center along distorted bars and bridges, triggers final bursts of star formation, then runs out or heats up. Without a cold, organized disk, density waves cannot sustain themselves. Over a few billion years, the chaotic intermediate shapes settle toward a rounder, puffier body. Astronomers expect the end state to resemble a large elliptical or a smooth, featureless lenticular. Milkomeda. The central regions become dense and kinematically hot, with stars moving on boxy, randomized orbits. The outskirts hold long shells and streams, faint signatures of the paths that led here, like echoes that take longer to fade. Throughout, the risk to individual star systems stays small. The odds of the Sun encountering a direct stellar pass close enough to strip planets remain low, though not zero. The larger hazard comes from cloud encounters and gravitational nudges that could shift the paths of comets in a star's distant reservoir. But the time between disruptive events remains vast, and life, if it exists then, will have had time to adapt or move. The background radiation environment changes in patches. Starbursts in compressed regions, quiet zones in others. So no single story rules the entire sky. The timeline resists human narration. Millions of years make up a single beat. The first clear sky change takes tens of millions. The passage and recoil extend over hundreds of millions. Full relaxation into the new form may take 5 to 10 billion years from the first deep pass. No living witness carries that memory, yet you share the same sheet of time. The atoms in your body will continue in other forms while this process unfolds. The scene you lie under tonight belongs to the same arc as the future arch of Milkomeda. What can be said for certain is that equilibrium is temporary here. The current spiral grace is not an eternal identity, it is a phase. The approach has already written a schedule for change in the overlap of dark halos and in the slow bleed of orbital energy to tidal debris. What looks empty between galaxies is not passive. It is the medium that couples them, so with each pass, more of the old organization dissolves and new structures appear that could not have formed otherwise. dense cores rebuilt, extended envelopes assembled from scattered stars, shells that mark turning points in the convergence. By the time the final coalescence has finished, the sky will hold fewer sharp dust lanes and more smooth gradients. Star formation will quiet as cold gas runs down, only to flicker where minor mergers and infall later feed the core. The central black hole will sit heavier, its sphere of influence larger, its past written in stellar orbits wound tight around it. The streams that once traced the outskirts will fade below naked eye thresholds, but remain in deep exposures as pale signatures, the last handwriting of the dance that ended the age of spirals here. You live early in that timeline, but not outside it. The faint smear already glows from your backyard on a clear night even now. The math of orbits has already assigned roles. The rest is only patience, measured not by calendars but by revolutions of a galaxy that will finish this act, long after our brief chapter has closed. You're back where we began, but now the ceiling above your bed reads differently. Those faint bands of light are not just stars, they're trails, long, cold remnants of small galaxies the Milky Way stripped and folded in. The gentle glow slipping past the curtains carries witness statements from systems that no longer exist. Each stream crosses the halo like a faded scar, a memory stretched thin until only motion remains. That means the calm you feel right now lives inside a structure made from captured orbits, stitched together by gravity into something that looks serene because the violence is spread across so much time. The connection isn't abstract. Your body holds proof. The iron-moving oxygen in your blood was packed into being when a star's core failed, and the shock front hurled new nuclei into space. The calcium in your bones condensed out of shells, blown off swollen old stars, drifting and cooling until it became part of a cloud that would turn into rock. The oxygen entering your lungs came from hot, short-lived stars that fused lighter elements and sent them into the medium between systems. That material mixed, settled into a disk, and kept cycling until your cells could form. There is no piece of you that didn't pass through at least one star, and often several, before the sun switched on. Scale makes the paradox sharp. You weigh almost nothing compared to the galaxy, and yet your awareness carries a map of it. From this bed, a small span of time contains an entire system's worth of motion. While you sleep, the sun sweeps you millions of miles around the center. While you breathe, clouds collapse somewhere into young stars and dissolve somewhere else under radiation. You're small, but you are the only way this room knows it sits inside a spiral galaxy assembled from ruins. Consciousness does not shrink the story. It lets the story be felt. Nothing waits for permission. The dark halo upholds the disk whether you think about it or not. Stars keep their orbits because most of the mass here doesn't shine. Spiral arms continue as waves in a rotating field of gas and dust. A nursery lights up along one segment as dense gas tips into collapse. Another turns quiet as newborns blow out the fuel that made them. Above the plane, hot outflows cool and fall back. Below it, a different patch heats and rises. All of it continues while alarms are set and silenced, while someone flips a pillow to the cooler side and drifts under. If you could listen in, you'd hear no rhythm you could hum, just a steady exchange that makes the next sunrise ordinary. That's the comfort. You don't need to hold the equations that describe the arms as density waves or parse the math of accretion flows near the core. The system predates your questions and will outlast them. The Milky Way assembled from smaller pieces and keeps reshaping itself on its own timescale. Your understanding can shift and deepen, but these processes proceed regardless. The night sky is an active ledger. The numbers add up whether anyone checks them. So, lying here, you can let the facts stand and let them be quiet. The galaxy you call home built itself by drawing in neighbors. Many of the stars up there started life elsewhere and now move on paths that remember their old homes only in their chemistry and direction. The disk lives inside a dark halo that keeps its rotation from tearing it apart. Gas cycles through fountains and chimneys, rising hot, cooling, and settling back as fuel. From that fuel, stars form, live, return material, and make the next round of stars and planets possible. That cycle made this room. Your place inside it has its own luck. The sun sits in a slower lane between larger arms, near a region where its speed matches the pattern speed of the spiral wave for long stretches. That means fewer disruptive crossings, fewer nearby explosions, and a long window for life to develop unharried. Planetary systems form often, but not all of them sit in neighborhoods with this mix of stability and material richness. Earth's long stretch of relative calm is not guaranteed anywhere. It's a condition this address provides. Even the future is folded into this present. Far ahead, our galaxy will reshuffle as the big neighbor across the sky drifts closer. Orbits will stretch and settle. The shape will change. The name we use might change too. But that distant chapter doesn't cancel this one. It places it. You're living in an era where the spiral still holds, where the central engine is quiet enough to let a disk carry on, where the sky contains records that careful measurements can read. That's not the beginning of the story or the end. It's a middle line that happens to be aware of itself. The awareness matters. You are a part of the mechanism, a temporary arrangement of the galaxy's atoms that can reflect on the galaxy's past. The same laws that curve a stellar stream around the halo also keep your brain's chemistry balanced enough to form a thought about it. That symmetry can feel like an odd coincidence. It's not. It's how complex matter behaves when given time and stable conditions. The universe didn't set out to notice itself, but here it does. So the next breath can be simple. Air in, oxygen to blood, iron carrying it, cells using it, heat leaving. Outside, cold hydrogen drifts in sheets and filaments and waits to be pressed into a different phase. That press comes from shock fronts and gravity, not purpose. The result looks like a star. Time goes by and that star returns enriched matter to the medium. Time goes by and some of that matter becomes another world, and on one such world, a room. Then a person who can look up and follow the line backward. There's nothing to fix in it. No command to extract. The facts don't rush you. They sit beneath the everyday shape of a night and give it depth. You are temporary warmth inside a structure made from stellar graveyards and long, slow winds. You are a chapter that knows it is one. Rest in the knowledge that you stand on atoms with long histories written by stars, that you float inside a system whose hidden mass holds it steady, that your small life is threaded through with events that took billions of years to make possible. Let the ceiling be a sky. Let the city around you fade until the only sound is your own breathing. Beyond the roofline, streams arc in silence. The disk turns without hurry. Somewhere, a cloud crosses a threshold and begins to fall inward. Somewhere else, a cluster's last bright members blow apart its chamber and open a path out of the plane. All of it runs on without judgment. All of it includes you.